Hello there and welcome to Science for Sleep, where curiosity gets comfortable, complicated science is allowed to take its time, and nobody is going to test you on any of this in the morning. Tonight, we're going somewhere rather unusual. We're going inside a black hole, at least as far as theoretical physics will allow us, and we're going to look at an idea called a Planck star. Now, the name is not a star in the ordinary sense. It is not a glowing ball of hydrogen like the Sun. It would not have planets orbiting around it. You could not point a telescope toward the night sky and say, "Ah, there goes one now." As far as we know, nobody has ever observed a Planck star. It is a hypothetical object, an idea that comes from attempts to understand what might happen to matter when a massive star collapses into a black hole and gravity becomes so extreme that our usual description of space and time begins to fail, which is already quite a lot to deal with before bedtime. The idea was proposed by physicists Carlo Rovelli and Francesca Vidotto in work connected with loop quantum gravity, one of the approaches physicists are exploring in the effort to understand gravity at the quantum level. In their proposal, collapsing matter might not continue toward an infinitely dense singularity. Instead, when the density becomes extreme enough, quantum effects of gravity could resist further compression and produce something like a bounce. From the point of view of the collapsing matter, this process could happen relatively quickly. From far outside the black hole, enormous gravitational time dilation could make the process appear to take an extremely long time. Strange combination is what makes the Planck star idea so interesting. Something could happen quickly inside a black hole while the outside universe waits for an enormous length of time. So before we go any further, where are you listening from tonight? Are you somewhere quiet with the lights low and the day mostly finished? Are you listening through headphones while everyone else in the house is asleep? Perhaps it is still early where you are, and you've simply decided that a discussion about quantum gravity is exactly what the evening was missing. And while we're checking in, consider another question. When you picture the inside of a black hole, what do you imagine? Maybe you picture a dark sphere with a tiny point at its centre. Everything falls inward, gets squeezed into that point, and that's the end of the story. That picture is common. It's also where things become difficult. General relativity, Einstein's theory of gravity, describes black holes remarkably well. It has survived an extraordinary number of experimental tests. It predicts effects that sounded almost ridiculous when they were first discussed, including gravitational waves, which were eventually detected a century after Einstein developed the theory. So when general relativity tells us that sufficiently concentrated matter can collapse into a black hole, we take that prediction very seriously. The trouble arrives when we follow the mathematics all the way into the deepest part of the collapse. Under the classical description, the matter can be driven toward a singularity, a region where quantities such as curvature become unbounded, and the theory stops giving us a normal physical description. People sometimes describe the singularity as a point of infinite density. That phrase is useful as a first approximation, but it can also create the wrong impression. A singularity is not simply a tiny object sitting peacefully at the centre of a black hole, waiting for visitors. In general relativity, the appearance of a singularity tells us that the classical description has reached a limit. Something has gone wrong with our ability to continue describing the situation using the same equations. The equations have brought us very far. Then they effectively place a sign in the road saying, "Beyond this point, please bring a better theory." Physics has several of these awkward boundaries. Newtonian mechanics works beautifully until you deal with speeds close to the speed of light, at which point relativity becomes important. Classical physics works beautifully for many everyday objects until you investigate atoms and particles, where quantum mechanics becomes unavoidable, and general relativity works extremely well for gravity on many scales. But when enormous gravitational effects are concentrated into an extremely small region, physicists expect quantum physics to become important too. That gives us the problem of quantum gravity. General relativity describes gravity in terms of space-time geometry. Matter and energy affect the geometry of space-time, and that geometry affects how matter moves. Quantum mechanics describes the microscopic world using a very different framework, one involving quantum states, probabilities, uncertainty, and effects that do not resemble ordinary objects moving around on a fixed stage. Both theories work exceptionally well in the situations where we can test them. The difficulty is getting them to work together in situations where both should matter. The deep interior of a black hole is one of those situations. The very early universe is another. Physicists have several approaches to this problem, and loop quantum gravity is one of them. It remains a developing theoretical program, and its ideas about black hole interiors are not established observational facts. Reviews of black holes in loop quantum gravity describe both substantial theoretical work and unresolved questions, particularly when discussing the fate of information and the final stages of black holes. Tinction matters throughout everything we're going to discuss. Planck stars are not something science has confirmed, they are something science is investigating. That may sound less exciting, but I think it makes the subject more interesting. There is a tendency, especially when talking about black holes, quantum physics, and the early universe, to turn every speculative idea into a dramatic announcement. Scientists discover what is inside black holes. No, they haven't. Physics proves there are other universes. Also no. New theory destroys everything Einstein believed. Einstein may remain undestroyed for another evening. What physicists actually do is propose models, calculate their consequences, compare those consequences with established theory, look for contradictions, improve the mathematics, and eventually ask whether nature gives us any way of checking the result. Sometimes an idea survives, sometimes it doesn't. Sometimes it spends several decades sitting on a theoretical shelf while everyone waits for an experiment clever enough to reach it. Planck stars belong in that uncertain but fascinating territory. The basic problem they're trying to address is easy to state. What happens when matter collapses and there seems to be nothing left to stop it? Consider an ordinary star. Gravity is always trying to pull the star inward. A star does not remain large simply because gravity has taken the evening off. Gravity is active all the time. What prevents the star from collapsing is pressure generated by processes inside it. For much of a star's life, nuclear fusion in its core provides energy that helps support the star against gravitational collapse. The balance is not static in the sense that nothing is happening. Quite the opposite. Huge amounts of energy are being produced. Matter is hot. Particles are moving. Radiation is pushing outward. Gravity is pulling inward. The star exists because these competing effects can maintain a balance. Our sun has been managing this arrangement for billions of years. Very dependable. No need to send a reminder. Eventually, however, stars change. Fuel in the core is used up. The internal conditions shift. What happens next depends heavily on the star's mass. Some stars end as white dwarfs. Others leave neutron stars. The most massive stars can undergo collapse that leads to black hole formation. And the important point is that nature has several ways of resisting compression before a black hole enters the picture. Quantum mechanics itself can provide pressure. A white dwarf is supported in part by electron degeneracy pressure, which comes from quantum rules governing electrons. A neutron star relies on related quantum effects and the behavior of matter at enormous nuclear densities. So quantum physics resisting gravitational compression is not by itself an exotic fantasy. We already know that quantum physics can help support extremely dense objects. The Planck star idea asks whether something comparable, though involving quantum gravity rather than ordinary quantum matter, could occur at densities far beyond those inside neutron stars. Imagine continuing the collapse. Gravity overwhelms one form of resistance after another. The matter becomes denser, distances become smaller, space-time curvature becomes stronger. At some point, classical general relativity predicts conditions so extreme that we approach the singularity problem. But perhaps that is not what nature actually does. Perhaps before the classical singularity is reached, quantum properties of gravity become important. That possibility is the starting point. The word Planck refers to a set of natural scales associated with gravity, quantum mechanics, and the speed of light. You may have heard of the Planck length. It is extraordinarily small, around 1.6 times 10 to the minus 35 meters. For comparison, a proton is enormously larger than the Planck length, and by enormously, I mean the kind of enormously where ordinary visual comparisons stop being very helpful. If you tried drawing both of them accurately on a piece of paper, you would require either a very unusual piece of paper or a serious discussion with whoever ordered the office supplies. There is also a Planck time, roughly 5.4 times 10 to the minus 44 seconds, and a Planck mass, along with Planck energy and Planck density. These quantities appear when we combine fundamental constants associated with quantum theory, gravity, and relativity. Physicists expect that around such regimes, our ordinary classical picture of space-time may no longer be sufficient. This does not mean we currently possess a complete experimental description of what space-time does at the Planck scale. We don't. It means that this is the scale where theories of quantum gravity are expected to become relevant. Loop quantum gravity approaches the problem by treating aspects of geometry itself as quantum. Instead of assuming that space-time remains smoothly divisible without limit, the theory leads to discrete geometric quantities at very small scales. That quantum structure is central to the way loop quantum gravity researchers explore extreme regions such as black hole interiors, and see why a collapsing object becomes interesting. If geometry has quantum properties, perhaps you cannot continue compressing matter and space-time in exactly the way classical general relativity suggests. The collapse may reach a regime where the classical prediction of continued compression is replaced by new quantum behavior. In the original Planck star proposal, the important threshold is connected to density. A black hole can be enormous compared with the Planck length, and still contain a region where the density has become high enough for quantum gravitational effects to matter. That is an important detail because the name Planck star can make it sound as though the entire object must be Planck-sized. That is not the proposal. The idea is that the relevant quantum gravity effects appear when the density reaches an extreme Planckian regime. Rovelli and Vidotto specifically argued that the onset of quantum gravitational effects is governed by density rather than simply by the overall size of the object. Out what that changes. In the classical picture, collapse proceeds toward the singular region. In the Planck star picture, collapse reaches an extreme density, quantum gravity becomes significant, and continued compression is resisted. The collapsing matter does not simply disappear. It does not need to be crushed into a mathematical point of infinite density. Instead, the collapse could reverse. A bounce. That word sounds almost too casual. You might imagine dropping a tennis ball. This is not quite that. We are talking about a hypothetical quantum gravitational transition in one of the most extreme environments that physics can describe. Still, bounce is useful because it captures the basic idea. Collapse does not continue forever. At some point, the inward evolution changes. The system begins moving toward expansion, and immediately we encounter a problem. If matter bounces inside a black hole, why don't we see it come back out? Black holes have event horizons. Once matter passes through the horizon, classical general relativity tells us that returning to the outside is not like turning a spaceship around. Inside the horizon, the geometry is arranged in such a way that continuing toward the black hole interior is as unavoidable as continuing toward tomorrow. You don't escape by firing a stronger engine. All future directed paths lead inward. So if the Planck star bounces, where does the expanding matter go? How could it ever become visible? And if the bounce happens quickly, why can a black hole remain in the sky for an enormous length of time? This is where gravitational time dilation enters the story. General relativity tells us that clocks do not all agree when gravity differs. A clock deeper in a gravitational field can run at a different rate relative to a clock farther away. This is not merely a strange feature near black holes. We measure gravitational time differences here on Earth. Modern technology has to account for relativistic timing effects. Near a black hole, however, the difference can become extreme. In the Planck star proposal, the collapse and bounce can be brief according to the internal proper time of the object, while appearing extraordinarily slow from an external perspective. That time difference is one of the defining features of the proposal. Any falling inward with the collapsing matter, you reach the extreme regime. Quantum gravitational effects become important. The collapse stops. A bounce begins. From your local perspective, perhaps the relevant process does not require an absurd cosmic duration. Meanwhile, someone very far from the black hole could describe an entirely different timescale. The outside universe might age dramatically while the interior process unfolds. That means the object can, in principle, have two very different descriptions depending on which clock you're talking about. This is not because one observer is wrong. Relativity has already taught us to abandon the idea that there must always be one universal clock governing every event everywhere. Black holes simply push that fact into a much more uncomfortable setting. And discomfort is something black holes are very good at. They bend light, they distort time, they hide regions of space-time behind horizons. They eventually brought quantum theory into an argument with gravity. Then Stephen Hawking showed that quantum effects imply black holes are not completely black but can emit thermal radiation, introducing a new set of puzzles about evaporation and information. At that point, the black hole had already done quite enough, but physics continued anyway. One attraction of Planck star models is that they offer a possible route toward avoiding the classical singularity, while also contributing to discussions about what happens to information associated with matter that falls into a black hole. The original proposal suggested that such objects could ease aspects of the black hole information problem, although this remains part of ongoing theoretical research rather than a settled solution. ARC explored whether transitions involving black holes and white holes might produce observable consequences. A white hole, in the mathematical language of relativity, is roughly the time-reverse counterpart of a black hole. Things can come out. They cannot enter in the ordinary way. You do not need to picture an actual glowing white sphere. The name is mostly there because physicists occasionally enjoy naming one difficult concept by reversing the name of another difficult concept. Some Planck star research considers whether a black hole could eventually undergo a quantum transition connected with a white hole phase. Researchers have even examined whether primordial black holes undergoing such processes could produce signals that astronomers might search for. Rovelli discussed the possibility of explosive decay of primordial black holes through quantum tunneling as a potential observational probe, while emphasizing that this belongs to theoretical investigation of quantum gravity. Stability is useful because quantum gravity has a serious experimental problem. The scales involved are extreme. Building a laboratory experiment that directly reaches the Planck regime is not something we currently know how to do. That leaves physicists looking toward places where nature may already have done the difficult part. The early universe, black holes, perhaps extremely dense astrophysical objects. Nature has a considerably larger research budget than we do. A collapsing star provides gravitational conditions no laboratory on Earth can reproduce. If quantum gravity leaves some observable trace in what happens to black holes, then astronomy might eventually give us information about physics that would otherwise remain inaccessible. But before we start searching the sky for exploding Planck stars, we need to slow down. There are several different ideas bundled together here. We have ordinary stellar collapse, which is well-established astrophysics. We have black holes, which are strongly supported by observation. We have Hawking radiation, a theoretical prediction built from quantum field theory in curved space-time, but not yet directly observed from an astrophysical black hole. We have quantum gravity, for which no complete theory has been experimentally confirmed. We have loop quantum gravity, a serious research program with specific mathematical results and open questions. And within this setting, we have Planck stars, which remain hypothetical. Keeping those levels separate is important. Otherwise, a perfectly reasonable theoretical proposal can slowly turn into there is definitely a bouncing object inside every black hole, usually somewhere between a headline and the third cup of coffee. We do not know that. What we know is that classical general relativity leads us towards singular behaviour in black hole interiors. We also know that quantum mechanics governs matter at microscopic scales. We have strong reasons to believe that a quantum theory of gravity is needed under sufficiently extreme conditions. What happens when we finally have that theory is the unresolved part. Maybe singularities are replaced by bounces. Maybe something quite different happens. Maybe loop quantum gravity captures the right structure. Maybe another approach does. The useful question is not, are Planck stars definitely real? The useful question is, what problem is the Planck star idea trying to solve, and what would have to be true for it to work? That gives us somewhere concrete to begin. And the beginning is not actually at the Planck scale. It is not inside a black hole. It is not even particularly quantum. It starts with something much more familiar. A star. A very massive star, still producing energy, still holding itself up against its own gravity, with nothing obviously unusual happening from one second to the next. For most of its life, the balance works. Gravity pulls inward, pressure pushes outward, then the fuel changes, the core changes, the balance begins to fail. And once a sufficiently massive stellar core loses the support that has been holding gravity back, the inward motion does not politely stop at the first inconvenient density. It continues. Electrons are forced into conditions they cannot maintain. Matter changes form. Nuclei are pushed into extraordinary states. A neutron star may form if the remaining core has the right mass and conditions. But if the collapsing core is too massive for even that support to hold, gravity keeps winning. At that stage, talking about a Planck star becomes impossible without first understanding exactly what is doing the collapsing, what forces have already failed to stop it, how an event horizon appears, and why general relativity seems to leave the matter with nowhere else to go. The star we left behind was still holding itself together, which sounds simple until you remember what a star actually is. It is an enormous amount of matter being pulled inward by its own gravity, while its interior becomes hot enough and dense enough to keep that collapse under control. For most of the star's life, the arrangement works remarkably well. Gravity pulls inward, pressure pushes outward, and the star remains roughly stable. This balance is called hydrostatic equilibrium. Our sun is doing it right now. Gravity is constantly trying to compress it, while pressure from the hot material inside resists that compression. Nuclear fusion in the core helps maintain the temperatures required for that pressure. Nothing about the sun is simply sitting there. It is an active system maintaining a balance every second. For a massive star, however, that balance eventually becomes much harder to maintain. A star begins most of its long life by fusing hydrogen into helium. The core is hot enough that hydrogen nuclei can overcome their electrical repulsion and combine. A small amount of mass is converted into energy, and that energy helps keep the star hot and supported against gravity. Hydrogen does not last forever. Once the hydrogen in the central region becomes depleted, the core begins to contract. As it contracts, it heats up. If the star is massive enough, the temperature rises until helium fusion can begin. Helium can then produce heavier elements, including carbon and oxygen. In a star like the Sun, the process does not continue through all the stages available to much more massive stars. But a sufficiently massive star can keep going. Carbon can participate in further reactions, then neon, then oxygen, then silicon. The exact sequence is complicated, and real stars are not neatly organized diagrams with one element politely waiting until the previous element has finished. Different burning processes can occur in different shells around the core. By the late stages of a massive star's life, the interior can develop a layered structure, with heavier elements concentrated toward the center and lighter element fusion occurring farther out. People often compare it with an onion. This is slightly unfair to onions, which are easier to understand and rarely collapse into black holes. The important point is that each new stage buys the star more time, but usually much less time than the stage before it. Hydrogen burning can continue for millions of years in a massive star. Later burning stages become progressively shorter. Near the end, some processes can occur on timescales of days, hours, or even less. The star has spent most of its existence in a comparatively steady condition, and then the final stages arrive with very little patience. Eventually, the core becomes rich in iron group elements, and iron creates a serious problem. Earlier fusion reactions can release energy when lighter nuclei combine into more tightly bound nuclei. That released energy helps maintain pressure within the star, but iron sits near the point where fusion no longer provides the same useful energy return. Trying to obtain energy by fusing iron into substantially heavier nuclei does not continue the star's previous strategy. The core has reached a point where the usual fusion process can no longer keep supplying enough support. Gravity, meanwhile, has not become tired. It has been waiting the entire time. As the iron core grows, it is supported partly by quantum mechanical effects involving electrons. Electrons obey rules that prevent identical particles from all settling into exactly the same quantum state. When matter is compressed, this creates a resistance known as electron degeneracy pressure. This is one of those occasions where quantum mechanics quietly prevents something enormous from collapsing. White dwarfs are supported by electron degeneracy pressure. A white dwarf can contain a mass comparable to that of the Sun compressed into an object roughly the size of Earth. That is already an extraordinary density. But electron degeneracy pressure has a limit. If enough mass is packed into the core, gravity becomes too strong for this form of support to maintain the structure. For a massive dying star, once the iron core reaches the critical conditions for collapse, the situation changes extremely quickly. The core begins falling inward. Not metaphorically. Matter is physically accelerating toward the center under gravity. As the density and temperature rise, atomic nuclei are exposed to increasingly extreme conditions. High-energy photons can begin breaking heavy nuclei apart, a process called photodisintegration. That makes the problem worse. Building those heavy nuclei during earlier stages involved energy. Breaking them apart requires energy again. So energy that might otherwise contribute to supporting the core is consumed in dismantling nuclei. It is rather like discovering that the emergency support system has decided to use the remaining electricity to take apart the building. At the same time, electrons are being forced into protons. Through electron capture, a proton and an electron can combine to produce a neutron and an electron neutrino. This reduces the number of free electrons available to provide degeneracy pressure. So several things happen together. Fusion has stopped being an effective source of support in the iron core. Photodisintegration absorbs energy. Electron capture reduces electron pressure. Gravity continues pulling inward. The core collapses. The speed of this collapse becomes enormous. What took millions of years to prepare can reach its critical stage in a fraction of a second. The central density rises toward values found inside atomic nuclei. That is when another form of resistance becomes important. The matter is becoming neutron-rich, and the behavior of nuclear matter changes dramatically at these densities. Neutrons cannot simply be compressed together without limit under ordinary neutron star conditions. Quantum effects and nuclear interactions provide resistance. The inner core stiffens. Material farther out is still falling inward. When that infalling material encounters the suddenly much less compressible central region, a shock wave forms and begins moving outward. This is part of the process behind a core collapse supernova. It would be convenient if we could say the shock simply races outward, throws off the star's outer layers, and everyone goes home. The real physics is less cooperative. The shock can lose energy as it moves outward. Breaking apart iron nuclei consumes energy, and neutrino production carries enormous amounts of energy away from the core. The shock may stall, rather than immediately producing a successful explosion. Understanding exactly how the stalled shock is revived has required decades of detailed simulations. Neutrinos are an important part of the story. During the collapse and the formation of the compact core, astonishing numbers of neutrinos are produced. They interact weakly with matter under ordinary circumstances, which is why enormous numbers of neutrinos from the Sun can pass through your body without causing any noticeable inconvenience. Inside a collapsing stellar core, however, the density is so extreme that even neutrinos become dynamically important. They carry away a huge amount of energy. Some of that energy can be deposited in material behind the stalled shock. Convection, turbulence, rotation, magnetic fields, and other effects can also influence the explosion. The details remain an active area of astrophysical research, but the broad result is straightforward. Sometimes the outer parts of the star are blasted into space in a supernova. The core remains behind. And now the question becomes what that core is capable of supporting. If the remaining compact object falls within the right range of masses and conditions, the collapse can stop as a neutron star. A neutron star is one of the most extreme objects we know exist. Take an object containing more mass than the Sun and compress it into a sphere only a few tens of kilometers across. The exact radius depends on the mass and on the still, not completely understood behavior of matter at tremendous density, but roughly speaking, you are dealing with something the size of a city containing a stellar amount of matter. A teaspoon of neutron star material, if you could somehow remove it while ignoring several major physical complications, would have a mass of billions of tons. This is why astrophysicists tend not to recommend neutron stars as table decorations. Their surface gravity is enormous. Their magnetic fields can be extreme. Many rotate rapidly. Some neutron stars produce beams of radiation that sweep through space as the object spins. If one of those beams repeatedly crosses Earth, we observe regular pulses and call the object a pulsar. For our discussion, however, the most important feature of the neutron star is not what it emits, it is what it represents. It represents another successful attempt by nature to stop collapse. The star's ordinary thermal pressure failed. Electron degeneracy pressure could not save the massive core. The matter was crushed into a neutron-rich state. Yet the collapse still found something that could resist gravity. For an appropriate mass, nuclear interactions and quantum mechanical effects allow a neutron star to reach a stable configuration, but now increase the mass. Imagine that the collapsing core is heavier, or imagine a neutron star that later gains matter from a companion star. Or two neutron stars merge, leaving behind a remnant too massive to remain stable. At some point, even neutron star matter cannot provide enough support. There is a maximum mass for a non-rotating neutron star, described theoretically through the Tolman-Oppenheimer-Volkoff limit. You do not need to remember the name. It sounds rather like a law firm specializing in extremely dense clients. The important point is that neutron stars cannot have unlimited mass. The exact maximum depends on the equation of state of ultra-dense matter, which describes how that matter responds to pressure and density. Physicists are still working to constrain this using nuclear physics, gravitational wave observations, pulsar measurements, X-ray observations, and other evidence. So there is no single simple number that applies in every realistic situation. Rotation can help support additional mass, composition matters, temperature can matter in newly formed objects. The behavior of matter at densities above those inside atomic nuclei remains uncertain, but the general principle is clear. Add enough mass, and eventually gravity wins again. This time there is no known stable stellar remnant waiting one step farther down the ordinary sequence. The core keeps collapsing. At this stage, it helps to be careful with a common picture of black holes. You may have seen an animation where a star becomes smaller and smaller until suddenly it turns into a black ball. That makes black hole formation look as though the matter reaches some special size and transforms into a new substance called black hole. That is not really what happens. A black hole is defined by the structure of space-time. As matter becomes sufficiently compact, a region can form from which signals can no longer escape to distant observers. The boundary of that region is the event horizon. For a simple non-rotating black hole, the characteristic radius associated with the horizon is the Schwarzschild radius. Compress the Sun into a sphere only a few kilometers across, and it would be inside its Schwarzschild radius. The Sun is not remotely close to doing this. It is not massive enough to end its life as a black hole through ordinary stellar collapse, so there is no need to make alternative weekend plans. For a much more massive collapsing core, however, conditions can become appropriate for a black hole to form. Once an event horizon appears, the situation changes in a fundamental way. Suppose you are safely far away. You can still see the effects of the collapsing object. Matter outside the horizon can emit light. Gas can heat up. Magnetic fields can produce powerful radiation. An accretion disk may eventually surround the black hole if material continues falling toward it. But signals originating from inside the event horizon cannot travel outward and reach you. Not even light can escape. This is not because light becomes tired. It is not because a mysterious force grabs photons and drags them backward. It is because the geometry of space-time itself has changed. Near an ordinary massive object, there are many possible paths through space-time. You can move inward. You can move outward. Light can travel away. Inside a black hole horizon, all future-directed paths lead farther inward. Going towards smaller radius becomes unavoidable in much the same way that, under ordinary circumstances, going toward the future is unavoidable. You can choose where to walk tomorrow. Choosing yesterday is more difficult. Inside the horizon, moving outward again is not simply a matter of having a powerful enough rocket. The structure of space-time does not provide an outward future path that takes you back across the horizon. This is where ordinary intuition begins to become unreliable. From far away, people sometimes imagine matter falling toward a black hole and being crushed against the event horizon. That is not what an infalling observer would experience. For a sufficiently large black hole, crossing the event horizon need not involve hitting a physical surface at all. There is no wall. There is no shell with a sign reading "Black hole begins here." Locally, you could cross the horizon without noticing a sudden boundary, assuming the black hole is large enough that tidal forces at the horizon are not immediately destructive and ignoring the surrounding astrophysical environment. Someone observing you from far away describes the situation differently. Because of gravitational time dilation and the behavior of outgoing light near the horizon, your signals become increasingly delayed and red-shifted. To the distant observer, you appear to slow and fade. They do not watch you casually cross the horizon and wave from the other side. From your own perspective, however, your clock continues normally. You cross the horizon in a finite amount of proper time. Then things become less comfortable. As you move deeper inside, tidal effects generally become stronger. Gravity acts differently on different parts of an extended object, because the gravitational field changes with position. Your feet might experience a different gravitational pull from your head. Near a stellar mass black hole, that difference can become enormous. The popular term is spaghettification, which sounds cheerful considering it refers to being stretched along one direction and compressed along others. Black hole terminology occasionally has a sense of humour that the actual black hole does not share. But tidal forces are not the central problem for the Planck star idea. The central problem is what the classical theory says happens after the horizon has formed. Keep following the collapsing matter. The radius continues decreasing. Density rises. Space-time curvature becomes more extreme. General relativity does not contain an ordinary pressure mechanism that suddenly appears at some tiny scale and announces that collapse has gone far enough. Under the classical equations, the evolution leads towards singular behaviour, and this is where the phrase "collapses too far" becomes useful. Not because there is a known cosmic safety line marked on a ruler. Rather, because the physical conditions eventually enter a regime where we have good reason to doubt that classical general relativity can be the complete description. We have seen this sort of limitation before. Imagine trying to explain an atom using only classical physics. You could learn useful things about electric charges. You could use classical electromagnetism successfully in countless situations. But eventually the atom forces you to use quantum mechanics. The failure would not mean classical electromagnetism was foolish. It would mean you had pushed it beyond the regime where it was sufficient. Black hole interiors may be doing something similar to general relativity. Einstein's theory describes gravitational phenomena with extraordinary success. It predicts the bending of light. It explains the orbit of Mercury more accurately than Newtonian gravity. It predicted gravitational waves. Modern GPS systems require relativistic corrections. Observations of black holes and compact objects continue to agree impressively with relativistic predictions. But a theory can be extremely successful and still be incomplete. General relativity is a classical theory. Quantum mechanics is not built into its basic description of space-time. Usually that is manageable. For the orbit of Earth around the Sun, nobody needs to calculate quantum fluctuations of space-time before deciding whether August comes after July. Gravity is weak enough, and the relevant scales are large enough that general relativity works extremely well. A collapsing stellar core is different. It gives us a route toward a place where an enormous amount of matter becomes concentrated into an increasingly small region. Now gravity is extremely strong. Distances can become extremely small. The density can become extraordinary. And the classical evolution heads toward a singularity. The word singularity is often presented as though physicists have discovered an actual, infinitely dense bead at the center of every black hole. That goes farther than the theory allows us to say confidently. A singularity in general relativity indicates that the classical space-time description becomes incomplete in a particular sense. Paths through space-time cannot simply be extended indefinitely in the usual way, and physical quantities associated with the geometry can become unbounded. The theory is telling us that something has reached its limit. What it does not tell us is what a complete quantum theory of gravity would put there instead. Perhaps the singularity remains in some form. Perhaps quantum gravity removes it. Perhaps space-time itself changes character. Perhaps there is a transition to another region. Perhaps the collapsing geometry eventually bounces. Those possibilities are where ideas such as the Planck star enter. And notice how many barriers gravity has already crossed before we get there. A normal star had thermal pressure. Gravity eventually defeated it. The collapsing core had electron degeneracy pressure. Gravity defeated that too. A neutron star can use quantum effects and nuclear interactions to resist further compression. Above a sufficient mass, gravity defeats that support. Then an event horizon forms, removing the possibility of an ordinary escape back into the external universe. Classical general relativity continues the collapse, so by the time anyone suggests a quantum gravity bounce, we're not trying to solve an everyday problem with exotic physics. We're asking what happens after every familiar mechanism capable of stopping gravitational collapse has already failed. This distinction is important because it prevents the Planck star from sounding like an arbitrary invention. The reasoning is not, black holes are strange, so perhaps there is a tiny magic star inside. The reasoning is that classical gravitational collapse leads to a regime where the classical theory itself becomes inadequate, and some physicists are investigating whether quantum properties of a spacetime could alter the final stages of that collapse. Loop quantum gravity is one attempt to describe those properties. Within that approach, geometry is not expected to remain perfectly smooth and continuous at arbitrarily small scales in the same classical sense. Areas and volumes acquire quantum properties, and under sufficiently extreme conditions those properties may matter. General relativity has already carried us through the collapse of a massive star, past the failure of ordinary pressure, past the limits of neutron star matter, and across the formation of an event horizon. Up to this point, Einstein's theory has done something remarkable. It has taken a complicated physical process and described what gravity does as matter becomes more and more concentrated. The problem begins when we keep following the collapse. There is no rule in classical general relativity that says the matter has now become sufficiently compressed and should stop. Once a sufficiently massive object has formed a black hole, the interior geometry continues directing the collapsing matter inward. The distances involved become smaller. The density becomes greater. The curvature of space-time becomes more extreme. Eventually, the theory leads us somewhere that is usually represented by one word: singularity. It is one of those scientific terms that sounds as though it explains the situation simply because it has a dramatic name. It does not. In fact, the singularity is the point where the explanation becomes much less comfortable. You will often hear that the singularity is an infinitely small point containing infinite density. That description appears frequently in popular explanations of black holes, and for a simple non-rotating black hole solution, it gives us a useful first picture of what the mathematics seems to be doing. But we need to be more careful than that. A singularity is not necessarily an object sitting somewhere inside space-time. It is not a tiny ball made of unusually dense material. It does not have a surface that you could approach, inspect, and then report back on, which is fortunate because the return journey would already be difficult. In modern general relativity, physicists often describe singular behaviour using something called geodesic incompleteness. The phrase sounds considerably worse than the idea. A geodesic is essentially the path followed by something moving freely through space-time. A planet following its orbit, a ray of light travelling through curved space-time, or an observer falling without firing a rocket can all be described using appropriate geodesics. Normally you would expect such a path to continue. An observer exists at one moment, then another, then another. Their world line extends through space-time as long as nothing physically ends their existence. But in a singular space-time, there can be paths that cannot be continued beyond a certain point, even though the traveller has experienced only a finite amount of time. The road simply stops, not because there is a wall, not because another object blocks the way. The space-time described by the theory has no further route to give you. That is a much more precise way of seeing the problem. Rather than imagining a mysterious marble of infinite density, imagine that the mathematical structure we're using to describe locations, times, distances, and motion becomes incomplete. You ask what happens next. The theory does not provide a next. That is why singularities make physicists uneasy. Physics is normally about evolution. Give a theory the state of a system now, and the equations tell you how that system behaves later. Throw a ball, and mechanics predicts its trajectory. Place a satellite near Earth, and general relativity can describe its orbit with extraordinary precision. Follow two black holes as they spiral together, and relativity predicts gravitational waves that instruments on Earth can detect. Then you enter the deepest part of gravitational collapse and ask the same innocent question. What happens next? And suddenly, one of our most successful theories has nowhere to take you. It is worth emphasizing how strange that is, because general relativity is not a fragile theory that fails whenever conditions become inconvenient. It has survived more than a century of testing. Einstein published the general theory of relativity in 1915. The central idea is that gravity is not simply a force pulling objects across a fixed background. Matter and energy affect the geometry of spacetime itself, and objects move through that curved geometry. The idea produced predictions that were different from Newton's gravity. Light passing near a massive object should bend. Clocks at different gravitational potentials should tick at different rates. The orbit of Mercury should behave slightly differently from the prediction of Newtonian mechanics. Disturbances in space-time should travel outward as gravitational waves. These effects have been tested. Relativity works. We use relativistic corrections in technologies such as satellite navigation. Astronomers observe light being bent by massive objects. Atomic clocks can measure gravitational differences in the passage of time. Gravitational wave observatories have detected signals from merging black holes and neutron stars. So when we say Einstein begins to struggle inside a black hole, we are not saying Einstein made a simple mistake. Quite the opposite. The theory works so well that we trust it enough to follow its predictions into regions we cannot directly visit, And when we do, the theory itself tells us that something extreme happens. The first black hole solutions appeared remarkably soon after general relativity was published. Carl Schwarzschild found a solution to Einstein's equations for the space-time outside a spherical non-rotating mass. There was an odd feature in the mathematics. At a particular radius, some quantities in the coordinates Schwarzschild used seemed to misbehave. For a long time, it was not obvious what this meant. Was there a physical singularity at that radius? Did space-time actually break there? Was it impossible to cross? Later work showed that this particular problem was caused by the choice of coordinates. The horizon itself was not the destructive singularity people had initially feared. A comparison may help. Imagine a map of Earth using latitude and longitude. At the North Pole, longitude becomes awkward. Every line of longitude meets there. You might look at the coordinate system and conclude that something terrible happens to the planet at the pole. But the North Pole is not physically broken. The coordinates are. You can stand there perfectly well, although you may want a coat. Something similar happens with the event horizon in the simplest black hole description. Use one set of coordinates, and the horizon can look mathematically troublesome. Use better coordinates, and the apparent problem disappears. Space-time continues through the horizon. An observer falling into a sufficiently large black hole can cross that boundary without encountering an infinitely curved wall. That discovery might seem reassuring. Perhaps the entire singularity problem was just a bad choice of coordinates. Unfortunately, the relief didn't last. The central singular behavior remained. Unlike the apparent problem at the horizon, the problem deeper inside could not simply be removed by choosing a more convenient coordinate system. Curvature itself could become unbounded in the classical solutions. That was more serious. Still, there was another possible escape. Perhaps these singularities appeared only because the early black hole models were unrealistically perfect. The Schwarzschild solution assumes spherical symmetry. Real stars are not perfectly spherical. They rotate. They contain magnetic fields. Their density is uneven. They may have companions. Material falls unevenly. Stars wobble, pulse, convect, shed matter, and generally refuse to behave like objects in introductory physics diagrams. Maybe the singularity appeared because mathematicians had imposed too much order on the collapsing star, disturbed the symmetry slightly, and perhaps the whole thing disappears. That possibility remained important until Roger Penrose approached the problem from a different direction in the 1960s. Instead of asking what happens in one perfectly symmetrical model, Penrose developed methods that could address gravitational collapse much more generally. One key idea was the trapped surface. Normally, if you have a spherical region and send light outward from it, at least some of those light rays should move toward larger distances. Light aimed outward goes outward. This seems like a modest expectation. In a sufficiently strongly curved region during gravitational collapse, however, gravity can become so extreme that even the light rays directed outward are forced toward decreasing radius. Both the inward-directed and outward-directed families of light rays converge. The surface is trapped. Once a trapped surface forms under suitable physical conditions, the geometry is telling you that collapse has gone beyond an important threshold. Penrose showed that, given certain assumptions, this leads to geodesic incompleteness. In other words, singular behavior was not merely a strange feature of a perfectly spherical black hole model. It could arise from realistic gravitational collapse much more generally. That result changed the conversation. Black hole singularities could no longer be dismissed easily as artifacts created by unrealistic symmetry. The result was important enough that Penrose received half of the 2020 Nobel Prize in Physics for showing that black hole formation is a robust prediction of general relativity. There is a subtle point here. The singularity theorem does not hand us a photograph of what sits at the centre of a black hole. It does not tell us that every singularity must be a literal point with matter compressed into zero volume. It does not tell us the final microscopic state of collapsing matter. What it demonstrates, roughly speaking, is that under certain conditions, general relativity produces incomplete space-time paths. Something in the classical description cannot be extended normally. This is why saying there is definitely a tiny point of infinite density inside every black hole goes beyond what we should confidently claim. Infinite values do appear in familiar black hole solutions, including quantities associated with curvature as the classical central singularity is approached. But infinity in a physical theory deserves suspicion. Physicists are not usually delighted when a calculation produces infinity. Imagine asking an engineer how much pressure a bridge can withstand and receiving the answer, infinite. You would probably seek a second engineer. When a theory predicts infinite temperature, infinite density, infinite curvature, or some other divergent quantity, there are several possibilities. Perhaps nature genuinely contains the strange behaviour. Perhaps the mathematical idealization has been pushed too far. Or perhaps the theory is missing physics that becomes important before the infinity is ever reached. That last possibility has happened before. Classical physics once produced serious problems when applied to thermal radiation. The mathematics led toward what became known as the ultraviolet catastrophe, predicting an unphysical divergence in the energy emitted at short wavelengths. The solution was not that nature had hidden an infinite amount of energy inside a warm object. The solution required quantum physics. The old theory had been asked to describe a regime where its assumptions were no longer sufficient. That history does not prove that quantum gravity removes black hole singularities. Nature is under no obligation to repeat its previous solutions, but it gives physicists a good reason not to interpret every infinity as a literal physical object. The singularity may be telling us more about the limits of general relativity than about the existence of actual infinities in nature, and there is an obvious reason to suspect that something is missing. General relativity does not include a full quantum description of gravity. That was not a problem Einstein solved when he developed the theory. General relativity is classical. Matter curves space-time according to Einstein's equations, and space-time has a geometry that evolves continuously. Quantum mechanics, meanwhile, describes the microscopic world in a completely different language. Particles are associated with quantum states. Physical quantities can have uncertainties. Fields have quantum fluctuations. The vacuum is not simply empty nothingness. Systems can exist in superpositions, and measurements are described using probabilities in ways that have kept physicists arguing pleasantly, and occasionally not so pleasantly for generations. Usually, gravity and quantum mechanics can avoid confronting each other directly. Take a baseball. Quantum mechanics applies to all the particles inside it, but you do not need to calculate a complicated quantum state every time someone throws the ball. Ordinary mechanics is good enough. Take Earth orbiting the Sun. General relativity gives a very accurate gravitational description. You do not need a quantum theory of space-time to predict sunrise tomorrow. The relevant scales allow us to use different theories for different jobs. Black hole collapse removes that convenience. An enormous amount of matter is being squeezed into an extremely small region. Gravity is no longer weak. The geometry is becoming highly curved. The densities become far beyond ordinary matter. Eventually, the scales at which quantum effects matter and the conditions where gravity is extreme begin to meet. Now we need both theories in the same room. They do not fit together easily. Quantum field theory can be used successfully on curved space-time when the space-time itself is treated classically. That approach leads to one of the most famous results in black hole physics, Hawking radiation. In the 1970s, Stephen Hawking showed that quantum effects around a black hole imply that black holes should have a temperature and emit radiation. A black hole can therefore lose mass over time. That was surprising. Classically, the event horizon seemed like the ultimate one-way boundary. Things fall in, nothing comes back out. But quantum theory changed the picture. For a large astrophysical black hole, Hawking radiation would be extraordinarily weak. The larger the black hole, the lower its Hawking temperature. A stellar mass black hole would take an absurdly long time to evaporate. Still, the conceptual effect was enormous. Black holes were no longer completely eternal objects in the simplest semi-classical picture. Given enough time, they could shrink. And that creates another problem. Imagine throwing something into a black hole. A book will do. Not because physicists have anything against books, but because a book contains organized information. It has particular atoms arranged in particular ways. Its pages contain words. Its physical state carries information about how the system was prepared. Once the book crosses the event horizon, an outside observer cannot retrieve it in the ordinary way. Fine. Perhaps the information remains hidden inside the black hole. But then the black hole emits Hawking radiation and gradually evaporates. If that radiation is perfectly thermal, and the black hole eventually disappears, what happened to the information about the book and everything else that fell in? Quantum mechanics strongly resists the idea that fundamental information is simply destroyed. General relativity appears to hide the information behind the horizon. Hawking evaporation seems capable of removing the black hole itself. Put the three ideas together and you have the black hole information problem. It remains one of the deepest puzzles in theoretical physics. And notice what keeps appearing in the middle of the argument. The interior. We can describe matter falling toward the horizon. We can study quantum fields outside the black hole. We can calculate properties related to Hawking radiation. But eventually we need to know what actually happens to the collapsing matter deep inside. If classical general relativity sends it towards singular behavior, then our description ends precisely where some of the most important questions become unavoidable. The singularity is not merely an inconvenient detail hidden at the bottom of the black hole. It affects the consistency of the entire story. What happens to matter? What happens to information? Does space-time end? Does something replace the singular region? Can the collapsing system reach another state? Does the horizon remain forever? Can quantum effects change the interior geometry before classical general relativity reaches its endpoint? These are not questions Einstein's original theory can answer by itself. And there is another reason the problem matters. Black holes are not the only place where general relativity produces singular behavior. Run the expansion of our universe backward using classical general relativity and, under appropriate conditions, you encounter another singular boundary associated with the Big Bang. Again, popular explanations sometimes turn this immediately into an infinitely dense point from which everything exploded. The actual situation is more careful. The classical equations indicate that our description becomes singular when extrapolated far enough backward. We do not know whether a complete theory of quantum gravity replaces that beginning with a bounce, a different quantum state, a boundary of some kind, or something we have not yet thought of. So the singularity problem sits at both ends of some of our most extreme applications of gravity. Collapse a star far enough and classical space-time becomes incomplete. Run cosmic expansion backward far enough and classical space-time becomes incomplete. General relativity seems to know exactly how to lead us toward the problem. It does not know how to take us through it. This is where quantum gravity enters, although saying those two words is much easier than constructing the theory. Physicists have spent decades attempting to develop a consistent description in which gravity and quantum physics belong to the same framework. There is no experimentally confirmed final theory of quantum gravity. Different approaches attack the problem from different directions. String theory is one, loop quantum gravity is another. There are approaches involving causal structures, asymptotic safety, emergent space-time and other ideas. They do not all agree on what space-time is at the deepest level. They do not all predict the same fate for black hole interiors, and none has yet given us the sort of decisive experimental confirmation that quantum mechanics or general relativity enjoys. That uncertainty is important. A Planck star is not what physics has proven exists inside the singularity. It is one proposal for what could happen when quantum gravitational effects become strong enough that the classical collapse is modified. Before we reach that proposal, however, we need to understand why physicists expect such quantum effects to become important at a particular kind of scale. Ordinary distances will not do. An atomic nucleus is already incredibly small, but even nuclear dimensions are enormous compared with the scales we're about to discuss. A proton is roughly around a femtometer across, depending on exactly what quantity you're describing. A femtometer is about 10 to the minus 15 meters, very small. The Planck length is roughly 10 to the minus 35 meters. That difference is 20 orders of magnitude. Take the difference between 1 meter and something 100 billion times smaller, and you begin to see why direct experiments become difficult. But the Planck length is not simply the smallest ruler mark in the universe, despite how it is sometimes described. We have not measured space-time and discovered tiny pixels exactly 1 Planck length wide. Instead, the Planck scale arises naturally when fundamental constants associated with gravity, quantum mechanics, and relativity are combined. Newton's gravitational constant tells us about the strength of gravity. Planck's constant is central to quantum physics. The speed of light connects space and time through relativity. Combine them in the right way, and characteristic units appear. Planck length, Planck time, Planck mass, Planck energy, Planck density. Those scales tell physicists roughly where our current separation between quantum theory and classical gravity becomes impossible to trust. And black hole collapse has just given us a natural mechanism for pushing matter toward exactly that kind of regime. Gravity takes a massive stellar core and compresses it. Ordinary thermal support fails, electron degeneracy support fails, neutron star support fails if the mass is high enough. An event horizon forms, classical collapse continues, the curvature increases, the density grows. Eventually asking what happens next means asking a quantum gravity question whether we intended to or not. This is the point where Einstein struggles. Not at the event horizon, not because black holes themselves contradict relativity. Black holes are among relativity's great predictions. The trouble lies deeper, where the theory points toward a singular behavior and loses the ability to provide a complete physical continuation. That distinction matters for everything that comes next. We're not looking for a theory to replace general relativity everywhere. There is no reason to throw away a theory that works extraordinarily well across planets, stars, galaxies, gravitational lenses, black hole orbits, and gravitational waves. A successful quantum theory of gravity should recover general relativity in the situations where general relativity already works. Just as relativity did not make Newton useless, Newtonian gravity still puts spacecraft where we need them in many calculations. Relativity tells us where Newton's approximation reaches its limits. Quantum gravity may eventually do something similar for Einstein. The Planck star idea takes that possibility seriously. It asks whether the collapse toward singularity might be interrupted before the classical endpoint is reached. Maybe space-time has a quantum structure that prevents arbitrary compression. Maybe there is a maximum meaningful density. Maybe the classical inward evolution changes when quantum geometry becomes dominant. Those statements are possibilities, not established facts. But at least now we can see why physicists are willing to consider them. Without quantum gravity, we reach an incomplete path. With quantum gravity, there may be another piece of the story. To find out why loop quantum gravity suggests that space itself might behave differently under extreme compression, we have to leave the comfortable idea that distance can always be divided into smaller and smaller pieces without consequence. The important number, about 0.000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000016 meters, is the Planck length. Written in scientific notation, it is about 1.6 times 10 to the minus 35 meters. The notation is much easier on the eyes. The size is not. We have already passed atoms, atomic nuclei, protons, and every distance that has any useful connection with ordinary experience. A proton is roughly around 10 to the minus 15 meters across. The Planck length is about 20 orders of magnitude smaller than that. 20 orders of magnitude is a difference of roughly 100 billion. So even an atomic nucleus, which already feels impossibly small, is enormous compared with the Planck length. That immediately creates a temptation. You may have heard someone say that the Planck length is the smallest possible distance in the universe, or that space is made from little Planck-sized cubes, or that if you could magnify space enough you would eventually see pixels. Those are interesting ways to introduce the subject, but none of them is an established experimental fact. We have never looked at space at the Planck scale. We do not currently have an instrument that can zoom down to 10 to the minus 35 meters and take a photograph. No microscope has found tiny squares of space-time. The Planck length is important for a different reason. It appears when three parts of physics that normally live rather separate lives are placed in the same calculation. Quantum mechanics gives us the reduced Planck constant. Relativity gives us the speed of light. Gravity gives us Newton's gravitational constant. Combine those constants in the appropriate way, and a natural length appears. The Planck length. Do the same thing differently and you can construct a Planck time, Planck mass, Planck energy, and Planck temperature. These are called Planck units. The Planck time is about 5.4 times 10 to the minus 44 seconds. That is approximately the time light would take to travel one Planck length in empty space. Again, it is tempting to say this is the shortest possible moment. We do not know that. It is better to say that these scales indicate a regime where quantum effects and gravity are both expected to become important, meaning our usual theories can no longer be treated as comfortably separate. That is exactly the problem the collapsing black hole has been pushing toward. To understand why, consider how physics usually divides its responsibilities. Quantum mechanics is excellent at describing extremely small systems. General relativity is excellent at describing gravity and space-time. In most situations, one of those descriptions can dominate while the other barely matters. Look at an electron in an atom. Quantum mechanics is essential. You need quantum states, probabilities, energy levels, and the rules governing particles. The gravitational attraction between the electron and the atomic nucleus is so weak compared with the electromagnetic interaction that gravity can usually be ignored. Now look at Earth orbiting the Sun. Gravity matters enormously. General relativity provides the more accurate description, although Newton's theory works extremely well for many calculations. You do not normally need to worry about Earth's centre of mass being in a complicated quantum superposition while calculating next year's orbit. Nature allows us to use different tools because the situations are so different. One theory handles the microscopic world, another handles gravity on large scales. Then a black hole takes an enormous amount of mass and compresses it into a very small region. That removes the separation. The microscopic and the gravitational are pushed together. Eventually, you reach a regime where you cannot honestly say, let's use quantum mechanics, but ignore gravity. Gravity is too strong. You also cannot comfortably say, let's use classical general relativity and ignore quantum physics. The scale is too small and the energy density too extreme. Something has to combine them. We do not yet have an experimentally confirmed theory that does this completely. That is quantum gravity. And the Planck scale is where physicists expect that missing description to become especially important. There is another way to see why. Quantum mechanics tells us that trying to confine something to a smaller region generally comes with consequences. Position and momentum are related through the uncertainty principle. The more tightly you try to localize a quantum object, the less straightforward its momentum becomes. If you want to probe smaller and smaller distances, you generally need higher and higher energies. Particle accelerators work on this principle. To investigate small structures, physicists accelerate particles to enormous energies and collide them. Higher energies can reveal shorter distance physics. That strategy has taken us very far. It helped reveal the internal structure of protons. It contributed to the discovery of new particles. Modern colliders can recreate conditions that did not naturally occur on Earth for most of its history, but keep increasing the energy while forcing it into a smaller region, and gravity eventually becomes impossible to ignore. Energy gravitates, mass gravitates. Concentrate enough energy into a sufficiently small region, and general relativity tells you that the geometry of space-time responds. Push the thought experiment far enough, and you encounter the uncomfortable possibility that the energy used to examine an extremely tiny region could itself strongly distort that region. At some point, the microscope begins interfering with the thing it is supposed to examine in a way that is not merely quantum mechanical. Gravity joins the experiment. This is one reason the Planck scale is so difficult. The usual strategy of simply building a more powerful microscope eventually runs into a theory problem, an engineering problem, and a rather serious energy problem at the same time. For scale, the Planck mass is surprisingly ordinary compared with the Planck length. It is about 2.2 times 10 to the minus 8 kilograms. That is roughly 20 micrograms, not stellar, not even particularly impressive by kitchen standards. A small grain or speck can have a mass in that general range. So why is it called the Planck mass? Because the important part is not simply the amount of mass. It is what happens if Planck scale quantities are combined. Concentrating roughly the Planck mass into a region near the Planck length would involve an astonishing energy density. The smallness and the concentration matter together. A grain of dust sitting on a table is not a quantum gravity laboratory, which is probably for the best. Cleaning would become much more complicated. When physicists talk about Planck density in discussions of gravitational collapse, they are describing matter and energy compressed to an extreme regime where quantum gravitational effects are expected to be unavoidable, and this point is especially important for Planck stars. A Planck star does not mean a star whose entire radius is exactly 1 Planck length. That would be a misleading picture. In the original Planck star proposal, the trigger for quantum gravitational behavior is associated with density. The collapsing object can still have a size much larger than the Planck length when its internal density reaches a regime where quantum gravity becomes important. So picture our collapsing stellar core again. It has already passed inside an event horizon. Classical general relativity continues driving the matter inward. The volume occupied by that matter decreases. The density rises. If nothing changes, the classical description heads towards singular behavior. But suppose space-time itself has quantum properties. Then continuing the collapse indefinitely may be like compressing matter while pretending atoms do not exist. At ordinary scales, a table looks continuous. You can run your hand across it and describe its surface as smooth. Move down to atomic scales, and that description becomes incomplete. The table is made from atoms, electrons, nuclei, electromagnetic interactions, and quantum states. The smooth surface was an excellent approximation. It was never the whole story. Loop quantum gravity asks whether something similar could be true of space itself. The name comes from the mathematical variables used to describe the gravitational field and from the way the theory developed. The technical structure is complicated, and fortunately nothing important tonight depends on learning the full mathematics. The basic idea we need is that when gravity is quantized in this approach, geometrical quantities such as area and volume do not behave exactly as they do in classical general relativity. In classical geometry, imagine measuring an area. You can have 1 square meter, half a square meter, a quarter, an eighth. Keep dividing, and mathematically nothing forces you to stop. The same principle applies to volume. A region can be made smaller, then smaller again, then smaller again. Classical geometry is continuous. Loop quantum gravity changes that description at the quantum level. Area and volume are represented by quantum operators, much as other measurable quantities are represented by operators in quantum mechanics. And those operators have discrete spectra. That means the possible outcomes associated with measurements of quantum geometry come in particular allowed values rather than forming an ordinary continuous range. This is where the popular phrase atoms of space comes from. It can be useful as long as we do not take it too literally. An atom of space is not supposed to be a tiny solid object floating inside some larger container called space. There is no little brick sitting somewhere with empty space around it. The geometry itself is what is being quantized. The relationships that define area and volume have quantum properties. One of the structures used to describe this is called a spin network. A spin network can be pictured as a network of links meeting at nodes. The links and nodes carry quantum information related to geometry. Very roughly, links are associated with contributions to area, while nodes are associated with volume. Do not imagine microscopic wires physically woven through the universe. The network is part of the mathematical description of quantum geometry. The picture becomes useful because it gives us a way to think about space-time without assuming that a perfectly smooth geometry exists all the way down. At large scales, the discrete structure would need to reproduce the smooth space-time of general relativity. That is essential. Any candidate theory of quantum gravity cannot simply announce that Einstein was wrong and begin again. It must explain why Einstein's theory works so well wherever we have tested it. Think again about matter. A glass of water looks continuous. You can describe waves on its surface using equations for a continuous fluid. Those equations work beautifully. They do not require you to track each individual water molecule. But go down far enough and the molecular structure matters. The continuous fluid description is an approximation that emerges when enormous numbers of molecules behave collectively. Something similar might happen with space-time. At scales relevant to planets, stars, and most black hole observations, geometry could behave as the smooth space-time described by general relativity. At extremely small scales, a quantum structure could become important. That does not mean space-time definitely works this way. Loop quantum gravity is a candidate theory. Its prediction of discrete spectra for geometrical quantities is a major feature of the approach, but we have not directly measured Planck scale quanta of area or volume. The distinction between mathematical result and experimental confirmation remains important. Still, this kind of structure changes how we think about gravitational collapse. Classical general relativity lets the geometry continue toward the singular regime. The variables describing curvature can grow without bound. Volumes can shrink toward the classical endpoint. But if geometry is quantum, the assumptions underlying that description may stop being valid before the endpoint is reached. This is not unique to gravity. Quantum mechanics regularly prevents classical reasoning from being extended without modification. Consider an atom. A naive classical picture might suggest that an electron orbiting a nucleus should radiate energy, lose its orbit, and spiral inward. If that classical reasoning were the whole story, stable atoms would be a serious problem. Quantum mechanics changes the allowed behavior. Electrons occupy quantum states. The atom does not behave like a miniature solar system. Nature does not follow the classical extrapolation into disaster because the classical model was incomplete at atomic scales. Something loosely similar could happen during gravitational collapse. Classical relativity says the collapse continues. Quantum geometry may introduce behavior absent from the classical equations. That still does not automatically give us a bounce. We have to be careful. Saying geometry is quantized is not the same as proving that every black hole becomes a Planck star. There are difficult questions about quantum dynamics, the interior geometry, horizons, the relation between different quantum gravity models, and how the semi-classical exterior connects to the deep quantum region. There are multiple approaches even within research related to loop quantum gravity. The details matter, but we can at least understand the motivation. If the classical singularity appears because we have extended smooth space-time into a regime where smooth space-time is no longer an adequate description, quantum geometry might remove the singular behavior. A useful comparison comes from neutron stars. When a normal star collapses, classical intuition about matter eventually becomes insufficient. You cannot treat the core as an ordinary gas being squeezed harder and harder. Quantum mechanics changes the situation. Electron degeneracy pressure can support a white dwarf. At still greater densities, neutron-rich matter and nuclear interactions become important. Each time gravity compresses matter into a new regime, physics that was previously irrelevant becomes decisive. A Planck star extends that pattern one stage further. Thermal pressure fails, electron degeneracy pressure fails, neutron star support fails. Classical spacetime itself is pushed toward its limit. Then quantum gravity may become the next piece of physics that cannot be ignored. There is a major difference, of course. We have observed white dwarfs, we have observed neutron stars, we have strong observational evidence for black holes. We have not observed Planck stars, so the progression is not a list of equally established objects. The Planck star begins where the confirmed story gives way to a theoretical proposal. That proposal depends on something sometimes described as quantum gravitational pressure. The phrase is convenient, but it should not make you imagine ordinary pressure like air pushing against the inside of a balloon. The idea is that quantum effects associated with gravity and geometry could oppose the continued classical collapse when the density becomes extreme. In related loop quantum gravity work, similar reasoning has been explored in cosmology. Classical general relativity, run backward toward the early universe, leads towards singular behavior. In loop quantum cosmology, some models replace the classical Big Bang singularity with a quantum bounce. A contracting phase reaches extreme density. Quantum geometric effects become important, and contraction changes into expansion. This result does not prove that black holes bounce. Cosmological models and collapsing stars are different physical systems, but it gives researchers a reason to examine whether quantum geometry might produce comparable singularity-avoiding behavior elsewhere. Now return to the matter inside our black hole. From the perspective of classical relativity, it continues towards smaller volume. Suppose the density becomes enormous. Not merely neutron star enormous. Not merely anything we can produce in a collider, a regime where the quantum structure of geometry itself matters. At that point, the equations describing smooth spacetime may no longer be appropriate. The collapse could encounter new quantum behavior. This is the point where the name Planck star begins to make sense. It is not named that way because someone has found a tiny new kind of shining star. It is named for the Planck scale regime involved in the proposed interior state. And something slightly surprising happens when we ask how large this region might be. You might expect Planck scale physics to require a Planck-sized object, but density depends on both mass and volume. A large amount of matter can reach Planckian density while occupying a region much larger than the Planck length. That was one of the key observations in the original Planck star proposal. Quantum gravity effects are triggered by extreme density, not simply by the total diameter becoming exactly 1.6 times 10 to the minus 35 meters. For a black hole formed from stellar matter, the hypothetical quantum region can therefore be tiny by ordinary standards, while still being vastly larger than the Planck length. This matters because it changes what the interior picture looks like. We do not have to imagine the entire mass of a collapsed star packed into a literal point. We do not even have to imagine it packed into one Planck-sized cube. Instead, the matter could reach a finite but extreme density. Then quantum gravitational effects could become strong enough to prevent further classical compression. If there is a maximum effective density in the relevant model, gravity cannot simply force the system through it using the same classical evolution. Something has to change. This is where the word bounce appears. But before getting there, it is useful to pause over what the Planck scale has done to our usual categories. We started with matter collapsing through space. That language assumes matter and space are clearly separate. Matter occupies locations. Space provides the distances between those locations. Time tells us how the configuration changes. General relativity already complicates that separation because space-time is dynamical. Matter and energy change its geometry. The geometry then affects the motion of matter. Loop quantum gravity goes further. The geometry has quantum states. Area has quantum properties. Volume has quantum properties. The container is no longer merely a passive container. If the theory is pointing in the right direction, the thing being crushed during extreme gravitational collapse is not just matter. The classical geometry used to describe the crushing is also reaching a regime where its ordinary description fails. That's why solving the singularity problem is harder than inventing a stronger material. There is no super-dense substance sitting at the centre and holding up the weight in the usual sense. The problem involves space-time itself, and this is also why the Planck scale does not mean everything suddenly becomes random. Quantum mechanics is probabilistic, but it is not lawless. Atoms have definite patterns of allowed energy levels. Quantum fields obey precise equations. The predictions can be so accurate that experiments match them to extraordinary precision. A quantum geometry, whatever the correct final theory turns out to be, would still have structure and rules. Quantum does not mean anything can happen. It means the classical quantities we're used to may no longer behave as classical quantities. Space may not admit arbitrary subdivisions in the same way. Geometry may fluctuate. Areas and volumes may possess discrete quantum values. The familiar idea of a smooth spacetime curve may only be an approximation that becomes excellent once you move sufficiently far above the Planck scale. This creates an odd situation inside the black hole. From far away, the black hole can be enormous. Its event horizon might be kilometers across, or millions of kilometers across for a supermassive black hole. General relativity can describe the exterior extremely well. Nothing about the horizon requires space-time to look grainy or violently quantum. Deep inside, however, the collapsing matter may enter a completely different regime. The same object can therefore contain very different scales at once: a large, relatively classical exterior, an extremely dense quantum interior. That helps explain why quantum gravity effects do not need to announce themselves dramatically at the event horizon. In the Planck star picture, the crucial change occurs much deeper inside, where density becomes extreme. The horizon may form in an entirely ordinary relativistic way long before the collapsing core reaches that condition. Someone watching the black hole from outside would not see a bright flash at the moment the internal density reaches the quantum gravity regime. They cannot directly see through the horizon anyway. Inside, however, the classical collapse may be approaching its limit. The matter continues inward. The density rises. The geometry reaches scales where its quantum structure can no longer be neglected. Then the inward evolution may cease behaving like the singular collapse predicted by classical general relativity. The natural question is obvious. What could actually stop it? Calling something quantum does not provide an explanation by itself. Why would quantized geometry resist the collapse? Why should the matter bounce instead of remaining in some extremely dense state? What does a bounce even mean inside an event horizon, where every ordinary future-directed path appears to lead inward? And if the process reverses, how can anything that has crossed a black hole horizon ever become part of the outside universe again? The collapsing core has now reached the regime where our ordinary description of smooth space-time may no longer be enough. Density has risen far beyond anything found inside a neutron star. The event horizon formed long ago. Classical general relativity continues to direct the collapse inward, but we have arrived at precisely the conditions where quantum gravity is expected to matter. This is where the Planck star proposal makes its central move. The collapse does not continue all the way to a physical state of infinite density. It stops. Then it reverses. That reversal is usually called the quantum bounce. The word bounce makes the process sound surprisingly simple. Drop a rubber ball onto the floor and it compresses briefly before springing upward. Gravity pulled it down, forces in the material resisted the compression, and the ball changed direction. A Planck star bounce is not supposed to work like that. There is no solid floor at the centre of a black hole. There is no hidden surface waiting for the collapsing matter to hit, and the proposal does not require the core to be made from some incredibly strong material that finally says, that's enough. The idea is that the physics governing space-time itself changes when the density becomes extreme enough. In the classical description, gravity continues compressing the matter because nothing in Einstein's equations supplies a mechanism capable of stopping the collapse before singular behavior is reached. In a quantum gravity description, that conclusion may no longer follow. The geometry itself has quantum properties. Those properties can modify the dynamics. Under the Planck star proposal, the modifications become strong enough at very high density to counter the continued collapse and produce a transition from contraction to expansion. Carlo Rovelli and Francesca Vidotto described the idea as a stage in gravitational collapse, where quantum gravitational effects oppose further compression. The density reaches the Planck regime, the classical singularity is avoided, and the collapsing system undergoes a bounce. That does not mean gravity switches off. It does not mean gravity suddenly becomes a normal outward force, and it definitely does not mean somebody has inserted a spring into the center of the black hole. Quantum gravitational pressure is a convenient phrase, but it is best treated as a description of the effective result rather than an ordinary pressure like the air inside a balloon. Earlier in the life of the star, pressure had a more familiar meaning. Hot gas resisted gravity. Radiation helped resist gravity. Electron degeneracy pressure could resist gravity. Dense neutron-rich matter could resist gravity. Those effects involved matter responding to compression. At the Planck star stage, the proposed effect involves quantum properties of geometry itself. That is a much stranger situation. Space is no longer merely the place where the compression happens. The behavior of space is part of what changes. There is an important precedent for this kind of idea within loop-based approaches to quantum gravity. In simplified cosmological models studied in loop quantum cosmology, classical general relativity can predict a singular beginning when the universe is evolved backward. Quantum geometric corrections can alter the high-density behavior and replace the classical singularity with a bounce. A contracting universe reaches extreme density. Quantum effects become important. The contraction stops. Expansion follows. That result does not prove that the interior of a real, astrophysical black hole behaves the same way. A homogeneous cosmological model is not a collapsing star. A black hole has horizons, complicated geometry, possible rotation, matter interactions, and many details that simplified cosmological models do not contain. Still, the cosmological examples show something useful. Within certain loop quantum gravity models, quantum geometry can produce effective behavior that prevents the unlimited compression predicted by classical general relativity. That gives researchers a reason to investigate whether gravitational collapse could experience something comparable. So let us follow the matter inward again. The stellar core has passed through the horizon. According to classical general relativity, reaching smaller radius is unavoidable. The matter continues compressing. The density rises. Eventually it approaches the regime where quantum gravity becomes important. At that stage, our usual picture of individual particles being squeezed closer together inside an otherwise classical space-time becomes increasingly inadequate. The space-time geometry itself participates in the quantum dynamics. The collapse slows relative to what the classical equations would predict. The quantum effects strengthen. At some extreme density, further compression is prevented. The core reaches a minimum size. Then the direction of its evolution changes. Instead of continuing towards smaller volume, it begins expanding. That is the bounce. Immediately we run into what sounds like an impossible problem. The expanding matter is still inside a black hole. A black hole interior is not an ordinary room from which you can leave once you have changed direction. Once an event horizon has formed, classical general relativity does not allow an object inside simply to turn around and fly back out. Inside the horizon, the geometry is arranged so that the future leads toward the interior. The problem is deeper than escape velocity. You sometimes hear that the escape velocity of a black hole exceeds the speed of light. That can be a useful introductory phrase, but it can also suggest that a sufficiently fast spaceship would almost escape. That is not the right picture. The event horizon is a causal boundary. Inside it, every future-directed path available to light and matter remains inside, so if a collapsing core bounces, it cannot simply retrace its route through an unchanged black hole geometry. Something about the geometry has to change as well. This point matters because otherwise a Planck star would not solve very much. Suppose matter falls inward, reaches an extreme density, bounces, and then remains trapped forever behind exactly the same horizon. You have avoided one part of the singularity problem, but you still need to explain the later evolution of the system. What becomes of the expanding core? What happens to the horizon? What happens as the black hole loses mass through Hawking radiation? Can information eventually return to the outside? These questions led to later developments of the idea involving transitions between black hole and white hole geometries. A white hole is a solution related, very roughly, to running a black hole solution backward in time. A black hole allows matter to enter, but prevents it from escaping once it is inside the horizon. A white hole behaves in the opposite causal direction. Matter can emerge from it, but ordinary matter from outside cannot simply enter in the usual way. No astrophysical white hole has ever been observed. They are mathematical possibilities within general relativity, not confirmed objects hiding between ordinary stars. Still, the idea becomes useful when thinking about a bounce. A collapsing black hole region points inward. An expanding white hole region points outward. Some quantum gravity models therefore explore whether the bounce could connect a black hole interior to a white hole interior. Matter collapses. The classical singularity is replaced by a quantum region. The geometry passes through a transition. Expansion occurs on the other side of that transition. In later work, Ravelli and collaborators explored the possibility that a black hole could undergo a quantum transition into a white hole. This should not be treated as a universally accepted prediction of loop quantum gravity. There are different models of black hole interiors, different assumptions, and significant unresolved questions. But it provides a concrete way to think about what bounce might mean. The object does not simply hit the center and travel backward through the exact same classical black hole. The geometry itself changes. That distinction also helps with another common misunderstanding. Sometimes the Planck star idea is described as though a black hole forms, immediately bounces, and explodes a moment later. From the perspective of the collapsing matter, the high-density phase may indeed be short. From the perspective of the outside universe, the story can take far longer. This is one of the strangest parts of the proposal. The difference comes from gravitational time dilation. We already know that clocks do not run at one universal rate. A clock at sea level and a clock at the top of a mountain accumulate slightly different amounts of elapsed time. GPS satellites experience relativistic timing effects that must be accounted for if the navigation system is going to tell you which road you're actually standing on, rather than developing increasingly creative opinions about it. Near a black hole, the differences become far more dramatic. Imagine two descriptions of the same collapse. One description follows the matter falling inward. That matter carries its own clock. The time measured along its path is called proper time. From that local perspective, crossing the horizon and continuing inward does not require an infinite amount of time. For a stellar mass black hole, the interval between crossing the horizon and reaching the deep interior can be very short. If quantum gravity causes a bounce, the local duration associated with that deep interior process could also be short. Now describe the system from far outside. The timing looks completely different. Signals climbing away from a strong gravitational field are redshifted. Processes near the black hole appear increasingly slowed when described relative to distant clocks. The relationship becomes especially extreme around the horizon. The Planck star proposal uses this difference in timescales in a rather clever way. The bounce can be quick locally while its consequences remain hidden from the external universe for an enormous length of time. That means a black hole could appear long-lived, even if the interior avoids the classical singularity through a relatively rapid quantum process. Think of two clocks. One falls with the collapsing matter, the other remains far away. The falling clock accompanies the core through the high-density regime. It does not need to wait for billions upon billions of years before anything happens locally. The distant clock, however, can accumulate a vastly greater amount of time before the full process becomes accessible to the external universe. This is not a magical slowing mechanism added specifically for Planck stars. The strange relationship between time and gravity already comes from relativity. The Planck star idea uses that existing feature to connect a short internal process with a long external lifetime. This solves an immediate conceptual problem. If quantum gravity becomes important quickly inside every newly formed black hole, why do black holes not immediately disappear? Because quickly depends on which clock you mean. Inside, the relevant quantum process can occur over a comparatively short proper time. Outside, gravitational effects can stretch the apparent duration enormously. It is rather like discovering that the most important scheduling disagreement in the universe is built directly into space-time. There is another subtlety here. A distant observer does not receive a live video feed from the bouncing core. Once matter has crossed the event horizon, no classical signal from that matter reaches the external observer. The external black hole can remain almost entirely ordinary from the perspective of someone far away. Its gravitational field can look like the gravitational field of an ordinary black hole. Matter can orbit it. Gas can form an accretion disk. Light can be strongly lensed. Two such objects can orbit each other, merge, and produce gravitational waves. The bizarre quantum event may be occurring only in the deep interior. This is important because any replacement for the singularity has to coexist with the fact that general relativity works very well around observed black holes. Astronomers have seen stars orbit the compact object at the centre of our galaxy. We have detected gravitational waves from black hole mergers. The Event Horizon Telescope has imaged horizon-scale structures around supermassive black holes. So a viable quantum gravity model cannot require every black hole to behave obviously unlike general relativity from the outside. Whatever strange physics occurs must somehow allow the familiar black hole exterior to survive, at least for the periods and conditions we observe. A tiny high-density core hidden deep inside provides one possible route. From outside, black hole. Deep inside, quantum region. That makes the phrase Planck star inside a black hole tempting. But even that phrase needs caution. A Planck star is not necessarily a separate object sitting at the centre, in the way a marble might sit inside a box. The entire space-time is part of the model. The distinction between the collapsing matter, the quantum core, the horizon, and the later expanding region depends on the geometry and its evolution. Still, as a mental picture, we can imagine a finite region of matter reaching extraordinary density without reaching infinite density. The classical collapse is arrested. The core bounces. For some period, that quantum region remains hidden behind the black hole horizon. Then the longer-term geometry determines whether and how it can become connected again with the outside universe. At this point, Hawking evaporation becomes relevant. Hawking's calculation tells us that black holes should emit thermal radiation. Very large black holes radiate extremely slowly. As they lose energy, their mass decreases. Their horizon becomes smaller. A stellar black hole would require a duration vastly greater than the current age of the universe to evaporate through ordinary Hawking radiation alone. So nothing dramatic is expected from one tonight. You may sleep without monitoring the nearest black hole weather report. But conceptually, evaporation changes the geometry over enormous timescales. The black hole becomes smaller. Eventually, the horizon could approach the scale where whatever quantum structure exists in the interior can no longer be ignored by the exterior description. The original Planck star proposal considered the possibility that the interior core retains information about the much larger mass that originally collapsed. Because the onset of quantum gravity effects depends on density rather than simply size, the core need not shrink all the way to a Planck-length object. That becomes important near the later stages of the black hole's evolution. The Planck star can be much larger than the Planck length, even while quantum gravity is essential to its structure. If the horizon eventually shrinks enough, the hidden quantum region may cease to remain hidden in the same way. Later, black-to-white hole models explore related possibilities in which quantum tunneling changes the causal structure and allows an expanding phase. Tunneling is another word that needs care. In ordinary quantum mechanics, particles can sometimes cross barriers that classical physics says they should not cross. This does not mean the particle secretly moves faster than light or punches a hole through the barrier. The quantum state evolves according to rules that allow outcomes unavailable in the equivalent classical description. In quantum gravity, researchers have asked whether space-time geometry itself could undergo an analogous transition. A classical black hole geometry would not transform into a white hole geometry through ordinary Einstein evolution. A quantum transition might permit something that classical evolution forbids. The system could tunnel from one geometric configuration to another, again hypothetical, again mathematically motivated, again not something astronomers have watched happen. The interesting part is what this does to the singularity. In the traditional classical picture, matter collapses and the future ends at the singular region. In the bounce picture, that endpoint disappears. Collapse reaches a maximum density. Quantum geometry dominates. The system crosses the quantum region. Expansion follows. The history continues. That last sentence has major consequences. If the history continues, then the matter that fell into the black hole has not simply reached a place where physics stops. Its quantum state can, at least in principle, remain part of the later evolution. That makes the Planck star idea relevant to the black hole information problem. Information could enter during collapse, remain encoded in the quantum gravitational state, and potentially reappear during the later expanding phase. This does not automatically solve the information problem. There are difficult questions about how information is stored, how much can be retained, how it is released, whether the process preserves the correct quantum correlations, how Hawking radiation participates, and whether the proposed remnants or white hole stages are stable. The phrase, "the information comes back out," is the beginning of a calculation, not the end of one. But replacing the singularity with a continuing quantum evolution at least removes one obvious place where the description previously stopped. The bounce also raises a strange question about what happens to everything that originally formed the black hole. Imagine the core of a massive star collapsing. Perhaps additional gas falls in later. Perhaps the black hole spends millions of years swallowing surrounding material. Maybe another black hole merges with it. From the exterior, the mass of the black hole can grow dramatically. Deep inside, all of that contributes to a system that classical relativity would send toward the singular regime. If the singularity is replaced by a quantum region, then the theory must somehow account for that entire history. This is not a tiny particle performing a neat laboratory bounce. It is potentially several solar masses, or millions of solar masses, participating in a quantum gravitational geometry. That sounds absurdly large for quantum physics because we are accustomed to associating quantum behavior with electrons and atoms. But quantum theory itself does not contain a rule saying large objects are exempt. Large systems appear classical because quantum effects tend to become extremely difficult to observe as interactions with the environment destroy delicate coherent behavior. A black hole interior at Planckian density is not an ordinary large object sitting in a laboratory. The geometry itself is extreme. Quantum gravity could therefore matter even though the total mass involved is enormous. This produces one of the most counterintuitive features of the whole idea. The object can be massive. Its horizon can be macroscopic. The deep core can be much larger than the Planck length. Yet the physics governing that core may still be fundamentally quantum gravitational. What matters is the regime of density and curvature, not whether the object looks small compared with a coffee cup. There is another reason the bounce should not be pictured too mechanically. We have been saying, collapse stops, then expansion begins, as though there is one universal clock and a clearly defined instant when everything changes direction together. Inside strongly curved space-time, that language is only an approximation. Different choices of time coordinate can describe the geometry differently. The actual quantum transition would have to be represented through the state of space-time and matter, not through a little stopwatch attached to the center saying, bounce now. For a sleep-friendly explanation, however, the simplified picture is enough. The core contracts. Classical gravity would continue towards singularity. Quantum gravity effects become dominant. The singular endpoint is avoided. An expanding phase replaces it. The geometry has to participate in that transition because ordinary matter cannot simply escape through an unchanged black hole horizon. The entire proposal rests on that change. And that means the most interesting object may not be the tiny dense core by itself. It may be the combination of two very different regions. Outside, a black hole that can behave normally for an astonishingly long time. Inside, a quantum gravitational process that may have already reversed the collapse. The external observer could spend ages looking at something that appears to be a conventional black hole, while the internal story has moved into an entirely different phase. This is where our intuition about what is happening now becomes unreliable. Suppose the bounce takes place in a short, proper time for the collapsing matter. Can we say the black hole is already bounced while we are still watching it from outside? Relativity does not give us one universal cosmic present that answers that question neatly. Different observers divide space-time into space and time differently. Near a horizon, those differences matter enormously. So asking what the black hole is doing right now may not have the simple answer we expect. What we can say is that the interior evolution and the external lifetime can occur on radically different timescales. That feature allows the proposal to have both a rapid quantum bounce and a black hole that persists for a very long time. Eventually, though, the outside story has to catch up with the inside one. If the bounce remains forever causally sealed away, then no telescope will ever distinguish a Planck star interior from another singularity-free model. To turn the proposal into physics that could one day be tested, researchers have to ask whether the internal transition leaves consequences outside the horizon. Could the black hole eventually convert into a white hole? Could energy be released? Could information return? Would the event look like an explosion? Would the wavelength of the radiation carry a signature of the black hole's original mass? Could small primordial black holes reach this stage within the present age of the universe? And before any of those questions, there is an even simpler one. If we look at a black hole today, apparently quiet, dark, and behaving almost exactly as general relativity predicts, could there already be a bounce Planck scale core hidden inside it? What then could the black hole actually be hiding? From the outside, the answer appears almost disappointingly simple. Once a black hole settles down after forming, much of the complicated history of the object that created it becomes difficult to see. The star may have contained layers of hydrogen, helium, carbon, oxygen, silicon, iron, and countless smaller details. It may have rotated unevenly. It may have possessed magnetic fields, convection currents, spots, eruptions, and an entire history of nuclear reactions stretching back millions of years. After collapse, an outside observer does not see a detailed record of all of that. For an isolated, stationary black hole in the standard classical picture, the exterior is characterized mainly by a small set of quantities: its mass, its angular momentum, and, if it has any significant net electric charge, its charge. Real astrophysical black holes are expected to have very little net charge because surrounding plasma tends to neutralize them, so in practice astronomers usually care mainly about mass and spin. That is an extraordinary simplification. Imagine collapsing two very different objects. One begins as a star mostly made from ordinary stellar material. Another, through some extremely ambitious engineering project, contains the same total mass and angular momentum, but is assembled from millions of different structures, computers, clocks, dictionaries, bicycles, and every missing television remote control in the observable universe. Allow both systems to collapse and settle into black holes with the same mass and spin. From sufficiently far away, classical general relativity gives you no simple way to determine which black hole came from which collection of material. The complicated details appear hidden. This idea is associated with what physicists informally call black hole, no hair behavior. The phrase does not mean a black hole literally has no structure at all, and the mathematical theorems come with specific assumptions. It means that stationary black holes in general relativity are remarkably simple when described from the exterior. A star can have almost unlimited visible personality. A settled black hole is much less talkative. Yet something uncomfortable happens when quantum mechanics enters the discussion. Quantum theory cares about details, not necessarily details in the everyday sense of remembering whether the collapsing star once had a large sunspot on a Tuesday afternoon, but details contained in the complete physical state of a system. Physicists usually use the word information here, which can be misleading because it sounds like we're talking about documents, photographs, or messages. Quantum information is more general. It includes the relationships, correlations, and precise state needed to distinguish one physical configuration from another. Take a simple deck of cards. A neatly ordered deck and a randomly shuffled deck contain the same cards and have approximately the same mass. If you melted both decks into identical-looking lumps of material, the original arrangement would become practically impossible to recover. Practically impossible is not the same as fundamentally erased. In ordinary quantum evolution, the details of the initial state are expected to remain encoded in the later state, even if they become scrambled beyond any realistic hope of reconstruction. Burn a written page and the letters disappear. Smoke rises. Heat spreads into the room. Ash remains. Recovering the original page would require absurdly precise knowledge of enormous numbers of particles. But the ordinary quantum description does not require the initial physical information simply to vanish from reality. A black hole creates a more serious problem because it does something ordinary burning does not. It places part of the system behind a horizon. Throw the page into a fireplace and the resulting particles remain part of the same accessible universe. Throw the page through an event horizon, and an observer outside loses direct access to whatever crossed it. At first, that may not seem like a paradox. Perhaps the information is simply inside. You cannot retrieve it, but it still exists. Your house key can be perfectly real while remaining inaccessible under a refrigerator. The arrangement becomes more difficult once Hawking radiation is included. In the 1970s, Stephen Hawking studied quantum fields around black holes and found that the combination of quantum theory and curved space-time leads to a remarkable prediction. Black holes should radiate. This does not mean material simply climbs back through the horizon. Hawking radiation arises from quantum fields in the black hole space-time. Popular explanations often describe particle-antiparticle pairs appearing at the horizon, with one falling inward and the other escaping. That picture can be useful as a rough illustration, but it is not the complete derivation and should not be taken too literally. The important result is that an outside observer can associate a temperature with a black hole. The black hole emits radiation with approximately thermal properties. Because the radiation carries energy away, the black hole loses mass. Its horizon becomes smaller. Given enough time, an isolated black hole can evaporate. The timescale depends strongly on mass. A black hole formed from a star would evaporate unbelievably slowly. Its lifetime from Hawking evaporation would be vastly longer than the current age of the universe. Supermassive black holes last even longer. Smaller black holes are hotter and evaporate faster. This gives black holes a peculiar life cycle. They can begin as products of collapse, remain enormous and cold for extraordinary periods, and then become progressively smaller as they lose mass. Near the final stages, the semi-classical description itself becomes uncertain, because the black hole reaches the regime where quantum gravity should matter, which is exactly where our hidden Planck star has been waiting. Before returning to it though, notice the problem Hawking evaporation creates. Suppose a black hole never evaporates. Information falls inside. You cannot reach it, but perhaps it remains stored somewhere in the interior indefinitely. That is frustrating, but not necessarily inconsistent with quantum mechanics. Now allow the black hole to evaporate completely. The exterior radiation, according to Hawking's original semi-classical calculation, appears thermal. Thermal radiation does not seem to contain the detailed correlations required to reconstruct everything that originally formed the black hole. The black hole shrinks. Eventually it disappears. The interior disappears with it. Where did the information go? That is the black hole information problem. It has occupied theoretical physicists for decades because several principles that work extremely well seem to be pulling in different directions. General relativity creates the horizon. Quantum field theory gives Hawking radiation. Quantum mechanics expects evolution to preserve information in a technical sense known as unitarity. Put the simplest versions of those statements together and something does not fit. Perhaps Hawking radiation actually contains subtle information that the first calculation does not reveal. Perhaps the event horizon must be understood differently in a complete quantum gravity theory. Perhaps the interior is encoded in exterior degrees of freedom, in a way ordinary spatial intuition misses. Perhaps a remnant survives. Perhaps the classical black hole geometry eventually undergoes a quantum transition. There are many proposals. No single experimentally demonstrated answer has yet told us exactly what happens inside an evaporating astrophysical black hole. This is one reason the subject can become confusing very quickly. You will sometimes encounter statements that the information paradox has been solved. There has certainly been major progress. Ideas from holography, quantum information, gravitational entropy calculations, page curves, and so-called islands have shown ways in which unitary evaporation can emerge in theoretical models. In several settings, calculations reproduce the behavior expected if information is ultimately preserved. That is important. It does not mean we now possess a universally accepted, experimentally verified description of what happens to information in every real black hole formed by a collapsing star. Even the interpretation of some of these calculations remains an active subject of debate. For our purposes, the safer conclusion is straightforward. Many physicists expect information not to be fundamentally destroyed. Exactly how the black hole space-time accomplishes that remains one of the central questions of quantum gravity. The Planck star idea offers one particular route: return to our collapsing matter. Instead of reaching a singularity where the classical description simply ends, it reaches an extreme but finite density. Quantum gravitational effects become strong. Collapse is halted. A bounce occurs. The physical state has not fallen off the end of space-time. There is a later state. That alone changes the information discussion. In the classical singular picture, everything falling inward eventually encounters the point where our description stops. In the bounce picture, the evolution continues through a quantum region. The collapsing material does not need to be erased at an infinite density endpoint. Its state can remain encoded in the quantum gravitational system. You can think of this as a kind of memory, although not a memory stored like files on a hard drive. There would be no folder inside the black hole labelled things swallowed in 3 billion BC. The memory would be contained in the physical state of the matter and geometry. Every object that falls in changes that state. Add mass and the black hole becomes more massive. Add angular momentum and its rotation changes. At the deeper quantum level, the complete state could contain far more information than those few exterior quantities reveal. This is an important distinction. Black hole looking simple from outside does not necessarily mean its complete quantum state is simple. A locked warehouse can have one address on the exterior while containing an unreasonable amount of furniture. Black holes take this problem considerably further because even the meaning of inside becomes complicated. The size of a black hole as judged from its horizon does not necessarily tell you, in a simple Euclidean way, how much spatial volume exists inside. In curved space-time, interior geometry can behave in ways that do not match the picture of a normal ball with an ordinary volume calculated from its surface radius. This becomes useful in black hole remnant proposals. A late black hole could have a small external horizon, while its internal geometry retains a much larger structure and a long history. That gives theorists more room, mathematically speaking, to ask where information might reside. The original Planck star proposal used a related idea. The quantum core appearing during collapse can be much larger than the Planck length, because the relevant trigger is density rather than size. The matter reaches the density where quantum gravity becomes important before being compressed into a literal Planck-sized point. Meanwhile, the black hole exterior remains large. For most of the black hole's lifetime, there can be an enormous difference between the horizon scale and the deep quantum region. The outside observer sees a black hole. The interior has already encountered quantum gravity. Hawking radiation slowly reduces the mass from the outside. That process may continue for an enormous duration. The horizon shrinks. Eventually, the difference between the scale of the horizon and the scale associated with the quantum region becomes less extreme. Now the question of escape becomes unavoidable. If the collapsing matter bounced long ago according to its own local clock, why is it still hidden? The answer cannot simply be that the matter needs more speed. Nothing inside an ordinary classical event horizon can decide to move outward and cross the horizon. The bounce, therefore, requires more than an object reversing its motion. The causal structure has to change. That is why white holes enter later versions of the story. A white hole is, in a simplified sense, the time-reversed counterpart of a black hole. A classical black hole region allows things to enter but not return to the external universe. A white hole region allows things to emerge. The mathematics of general relativity contains white hole solutions, but there is no observational evidence that ordinary astrophysical white holes exist. The Planck star scenario does not need to claim that the universe is full of naturally formed classical white holes. Instead, some versions propose that quantum gravity could permit a transition from a black hole geometry to a white hole geometry. The black hole does not open a door in its event horizon. The geometry itself changes into a configuration with different causal behavior. This is why the word escape can be misleading. Imagine an insect trapped inside a sealed jar. If the insect later appears outside, you might ask how it crossed the glass. Did it break through? Did someone open the lid? A black to white transition is stranger than either option. It is more like the space-time definition of inside and outside changes as the system evolves. The classical horizon is not treated as an eternally fixed wall. Quantum gravity modifies the global history of the object. This remains theoretical. We do not yet know whether real black holes undergo such transitions. We do not know that every collapsing star produces a Planck star. We do not know whether a white hole stage would be stable. We do not know precisely how information would be released. Those are not small missing details. They are central parts of the problem. Yet the proposal provides a logical sequence that avoids simply dropping the information into a singularity. Matter collapses. A horizon forms. The interior reaches extreme density. Quantum gravity prevents the singular endpoint. The state continues through a bounce. The black hole remains externally long-lived. Hawking radiation gradually removes mass. A later quantum transition changes the geometry. Information stored in the interior may then become connected again with the external universe. There are several ways this final stage could be modelled. One possibility involves a relatively compact white hole remnant with a surprisingly large interior. From the outside, such an object could be tiny. Inside, its quantum geometry could retain information associated with the much larger black hole that existed earlier. That sounds almost like fitting the contents of a warehouse into a shoebox. Ordinary geometry would object. Curved space-time is under no obligation to arrange volume the way a shoebox does. A small exterior area does not automatically imply a simple small interior. Rovelli and Vidotto have explored whether small black hole or white hole remnants with large interiors could remain stable for long periods and preserve information. This is not the only remnant idea in quantum gravity, and remnants come with their own theoretical difficulties. If a tiny object can retain an enormous amount of information, physicists have to explain the relevant quantum states, their stability, how the object interacts with its surroundings, and why such remnants do not produce unwanted consequences elsewhere in physics. Moving the information from a singularity into a remnant does not end the conversation. It changes the conversation. There is also a more immediate possibility. Perhaps information begins returning through Hawking radiation before the final stage. Modern approaches to the information problem often expect the radiation not to remain perfectly independent of the black hole's internal state forever. Tiny correlations could encode information. A photon arriving after an unimaginable amount of time would not carry a readable sentence saying, "This used to be part of a star." The information would be distributed through correlations among the quantum states of the radiation. Recovering it could require measurements so precise and complicated that no practical observer could ever perform them. Physics does not require information preservation to be convenient. A shredded document still contains its original arrangement in principle if you retain every fragment and know how to reassemble it. A black hole may prefer considerably more aggressive shredding. This raises an important question for Planck stars. Does the quantum core need to store all the information until the black hole's final transition? Or does some information gradually appear in the Hawking radiation while the core retains only part of the story? Different approaches to the information problem answer questions like this differently. The original Planck star proposal argued that avoiding the singularity and allowing a long-lived quantum core could alleviate the paradox. Later, black-to-white hole work explored how a surviving interior and a white hole phase might carry information through the full evolution. These ideas should not be confused with the claim that the problem has been conclusively solved. They are candidate mechanisms. That makes the word memory useful if we use it carefully. A black hole may have very little classical hair, but that does not mean its quantum state has forgotten how it was made. The external gravitational field can be simple, while the full quantum description contains detailed correlations. The horizon hides those details from ordinary observation. Evaporation changes the horizon. Quantum gravity may change the interior. If information is preserved, then somewhere within that combined process the apparently lost details must remain represented. This is where entropy gives another clue. Black holes have entropy. The Bekenstein-Hawking relation tells us that black hole entropy is proportional to the area of the event horizon, rather than to the ordinary volume we might expect from familiar thermodynamic systems. That discovery is one of the deepest indications that gravity, quantum theory, and information are connected. A black hole with a larger horizon has greater entropy. As the black hole evaporates and its area decreases, the entropy associated with it also decreases. If the entire process is unitary, the information cannot simply disappear along with the shrinking area. It has to be represented somewhere in the combined state of the black hole and its radiation. This expectation is often illustrated using the Page curve. Imagine tracking the quantum entanglement associated with the Hawking radiation as evaporation proceeds. In a unitary picture, the radiation entropy does not simply rise forever until the black hole disappears. It eventually has to turn over in the appropriate description, indicating that the later radiation is correlated in a way that allows the final state to remain consistent with quantum mechanics. Recent theoretical work has found ways to reproduce such behavior in gravitational models. That is a substantial advance. However, translating those insights into a complete microscopic story for a realistic collapsing black hole remains difficult. Planck stars approach the problem from the interior side. Rather than beginning with the radiation and asking how information is encoded outside, they begin with the fate of the collapsing matter. Do not destroy it at a singularity. Allow quantum geometry to continue the evolution. Keep an interior state through the long black hole phase. Then determine how that state connects with the exterior as evaporation and quantum transitions change the space-time. That approach has an appealing continuity to it. The star does not collapse into mathematical oblivion. The matter enters a new regime. The geometry stores a history. The exterior hides that history. Evaporation slowly changes the conditions. Eventually, the hidden region may no longer remain hidden in the same form. There is still an enormous issue we have been quietly stepping around. How long is eventually? A stellar black hole can survive for a duration so large that the present age of the universe barely registers by comparison. Yet the proposed bounce inside can happen over a relatively short amount of proper time. That leaves us with two descriptions of the same object that seem almost impossible to reconcile. For the deep interior, the collapse and bounce may be relatively quick. For the distant universe, the black hole can remain there long after its parent star, its galaxy, and perhaps most familiar structures have changed beyond recognition. The explanation depends on the way gravity changes the relationship between clocks. Near a black hole, time measured along one path does not have to match time measured along another. The difference is not an optical illusion. It is built into the geometry. To understand how something brief can remain hidden for ages, we need to stop thinking about one clock governing the entire system. One clock stays far from the black hole, somewhere gravity is relatively weak. The other clock travels inward with the collapsing matter. At first, there is nothing particularly dramatic about comparing them. Both clocks count seconds. Both are perfectly good clocks. Neither one is broken. Yet as the falling clock enters a stronger gravitational field, the amount of time recorded by the two clocks begins to differ. From far away, the clock deeper in the gravitational field runs more slowly. This is gravitational time dilation, and unlike the hypothetical Planck star, gravitational time dilation is established physics. It is a prediction of general relativity that has been measured many times. Clocks at different heights above Earth do not accumulate time at exactly the same rate. The difference is tiny in everyday life, but modern atomic clocks are precise enough to measure it. Your head and your feet do not age at precisely the same rate when you are standing upright. The difference is far too small to rescue anyone from an upcoming birthday, but it is real. Move away from Earth and towards something much more compact, and the effect becomes stronger. A neutron star produces a much deeper gravitational field than Earth. A black hole pushes the situation to its extreme. That is where the modest disagreement between two clocks becomes central to the Planck star idea. Before going near the horizon, it helps to remove one common misunderstanding. Gravitational time dilation does not mean that a person near a black hole feels their own time slowing down. Suppose you are carrying the falling clock. Your watch still ticks normally. Your heartbeat feels normal. If you count to 10, you do not hear your own voice stretching into a 10-year speech. Your thoughts proceed normally. Chemistry proceeds normally. Every physical process occurring locally with you uses the same local time. You do not look at your watch and see the second hand struggling through syrup. The strange effect appears when clocks following different paths through space-time are compared. Your clock measures your proper time, the time accumulated along your own route through space-time. A distant observer follows a different route. Their clock measures a different proper time. General relativity does not require those two accumulated times to be equal. That is the first idea we need to become comfortable with. There is no hidden master clock somewhere in the universe issuing one official second to everyone. Newton's picture gave us something close to that. Time flowed universally. You could imagine clocks spread throughout the universe, perfectly synchronized, all agreeing about how much time had passed. Einstein removed that privilege. How much time passes depends on the path taken through space-time and on the gravitational environment along that path. Normally the difference is small enough to ignore. Near a black hole, ignoring it becomes a poor decision. Imagine that our distant clock remains comfortably far from a non-rotating black hole. The other clock is held stationary closer to the horizon. Holding it stationary is important. The clock is not falling freely. Some impossible support system, perhaps a rocket with very ambitious fuel reserves, keeps it hovering at a fixed distance from the black hole. The closer that clock is held to the horizon, the more slowly it runs relative to the distant clock. Move it closer still, and the difference becomes greater. In the idealized Schwarzschild description of a non-rotating black hole, a stationary clock cannot actually sit on the horizon. Maintaining a fixed position closer and closer to that boundary requires greater and greater acceleration. At the horizon itself, the idea of simply hovering there breaks down. So when people say, time stops at the event horizon, the statement needs qualification. Nothing crossing the horizon experiences its own time stopping. The phrase usually refers to how the process is represented relative to a particular distant time coordinate and to the behavior of signals sent outward from near the horizon. Those signals become increasingly redshifted. Their wavelength stretches, their energy decreases, they arrive increasingly delayed. An observer far away does not watch an infalling astronaut reach the horizon, pause dramatically, and remain visibly frozen there forever, like someone whose video call has failed at an unfortunate moment. The astronaut's light becomes weaker and redder. Very quickly, the image becomes effectively impossible to observe. From the astronaut's point of view, however, the horizon can be crossed after a finite amount of proper time. For a sufficiently large black hole, there may be no sudden local event marking the crossing. No alarm sounds, no physical shell is struck. Nothing nearby has to announce, "You're now inside." The astronaut simply continues falling. That difference between distant description and local experience is already strange enough. Now place a collapsing stellar core into the same geometry. The matter falls inward. A horizon forms. The material passes into the black hole interior. According to classical general relativity, the collapse continues towards singular behavior. According to the Planck star proposal, quantum gravity eventually becomes strong enough to halt the collapse and produce a bounce. And now we have to ask a very particular question. How long does that take? The answer depends on whose time you mean. For the collapsing matter, the journey from ordinary stellar dimensions into the deep black hole interior does not require the vast lifetime that an external black hole may appear to have. The local proper time can be relatively short. The matter falls, the density rises. The quantum gravity regime is reached. The bounce occurs. Nothing about that local description requires the collapsing material to spend trillions upon trillions of years patiently waiting at the center. Yet from the outside, a black hole can persist for an enormous period. That apparent contradiction is not an unfortunate detail in the Planck star picture. It is one of the main features that makes the proposal possible. Rovelli and Vidotto's original Planck star model emphasized exactly this separation. The high-density stage can be brief in the proper time associated with the collapsing system, while corresponding to an extremely long duration when described from outside because of the gravitational relationship between the interior and distant observers. So the black hole can hide a process that, locally, has already moved far beyond ordinary collapse. The outside universe does not need to witness the bounce immediately. That gives us a useful mental experiment. Imagine that you and a friend begin with synchronized clocks before the collapse. Your friend remains far away. You travel with the collapsing material, protected by an entirely fictional spacecraft, because realistic survival is not the purpose of the exercise. Your friend watches from a safe distance. Your routes through space-time are now completely different. As you approach the horizon, signals you send outward become increasingly redshifted. Your friend receives them more slowly. Eventually the signals become so weak and delayed that you effectively disappear from view. You, meanwhile, continue inward. Your clock keeps ticking. You cross the horizon. You reach the deeper interior. Under the Planck star hypothesis, the collapse eventually encounters quantum gravitational effects and reverses. From your local point of view, the relevant interval can be modest compared with the age of the black hole as judged outside. Suppose you could somehow ask your distant friend what time it is at the corresponding stage of the external evolution. There is no simple, universal, corresponding moment that both of you must agree upon. That is precisely the difficulty. Relativity has taken away the global present we instinctively want to use. This is important because phrases such as the Planck star has already bounced inside the black hole can make the story sound more definite than it is. Already according to which slicing of space-time, already relative to which observer, already according to which clock. Near a black hole, the question, what is happening there right now, is not always as straightforward as it sounds. At home, we get away with pretending that now is universal. Someone in the kitchen and someone in the next room can agree that it is 11:30 p.m. and move on with their lives. Relativistic differences between them are negligible. Stretch the situation across a strongly curved black hole space-time, and the assumption becomes unreliable. The Planck star scenario, therefore, is not simply telling us that one clock is slow and another is fast. It is describing a geometry in which the relationship between internal and external evolution can be enormously distorted. This helps answer the question that has been following us since the bounce was introduced. Why doesn't a Planck star bounce and immediately explode? Because the local bounce and the externally observable aftermath are not the same event described by one universal clock. The interior transition may occur over a short, proper timescale, while the exterior remains black hole-like for a far longer interval. Later black-to-white hole models develop this further. Instead of treating the external delay as only the familiar time dilation of a clock hovering near a horizon, they consider a genuine quantum transition of the space-time geometry. The black hole persists semi-classically for a long period, while quantum effects that are individually small may accumulate until the classical black hole configuration is no longer the full description. Haggard and Ravelli showed a model in which the geometry is classical outside a finite quantum region, while a long quantum timescale controls the eventual black-to-white hole transition. That distinction is worth keeping. Popular explanations can make the entire Planck star lifetime sound like ordinary gravitational time dilation alone. The full theoretical situation is more complicated. Gravitational time dilation explains why different clocks in strong gravity accumulate different amounts of time and motivates the enormous separation between local and distant descriptions. But the lifetime of a proposed black-to-white hole transition depends on the quantum gravity model. Researchers have explored different timescales and different geometries. There is no experimentally confirmed stopwatch reading that says every black hole waits exactly a particular number of years before becoming a white hole. We do not know whether real black holes undergo the transition at all. Some models have proposed lifetimes scaling differently from the usual Hawking evaporation time. Some later work modified earlier scenarios after concerns about stability and consistency. That is exactly what theoretical research is supposed to do. Someone proposes a model. Other physicists ask uncomfortable questions. The model changes. More uncomfortable questions arrive. Eventually, nature is expected to settle the disagreement, although nature has so far declined to provide convenient access to the inside of a black hole. The conventional Hawking evaporation timescale gives us one useful comparison. For a non-rotating black hole evaporating only through Hawking radiation in an otherwise empty environment, the lifetime grows very rapidly with mass, roughly with the cube of the mass in the simplest treatment. Double the mass, and the lifetime is not merely doubled, it becomes much longer. A black hole with a mass comparable to the Sun would survive for a duration enormously greater than the current age of the universe. The universe is about 13.8 billion years old. That already feels ancient. A stellar black hole's Hawking lifetime makes 13.8 billion years look less like old age and more like the universe checking whether the alarm has gone off yet. This is why we do not observe ordinary stellar black holes shrinking noticeably from Hawking evaporation today. Their temperature is extremely low. The cosmic environment currently bathes them in radiation warmer than their own Hawking temperature, depending on their mass and surroundings. The very long future of black hole evaporation belongs to an era far beyond ordinary stellar evolution. Planck star and black-to-white hole scenarios ask whether quantum gravity introduces another relevant timescale. Perhaps the quantum transition occurs before standard Hawking evaporation would reach its final semi-classical stage. Perhaps the later remnant behaves differently. Different versions of the proposal examine different possibilities. For us, the critical point is not choosing one precise lifetime. It is understanding that a short internal process and a long external history are not contradictory in relativity. Consider an even simpler example away from black holes. Two identical clocks begin together. One remains on Earth, another travels at very high speed and eventually returns. Special relativity predicts that they can show different elapsed times when reunited. Neither clock malfunctioned. Each correctly measured the time along its own path. This is the principle behind the famous twin scenario. A traveller moving near the speed of light can experience less proper time than someone who remains behind. General relativity adds gravity to the story. Now, the path through space-time and the gravitational environment both affect the accumulated time. Black holes combine these effects in extreme ways. The lesson is not that time is fake. The lesson is that elapsed time belongs to trajectories through space-time rather than to a single universal background. That idea gives the Planck star somewhere to hide. From the local perspective of the collapsing core, the quantum regime may be reached relatively soon. From the distant universe, the object can remain associated with a black hole exterior for ages. The horizon separates the regions causally. The exterior provides very little information about the rapid internal history. You can orbit the black hole. You can measure its mass. You can study the motion of nearby gas. You can detect gravitational waves if the black hole merges with another compact object. None of those observations automatically tells you whether the classical singularity exists deep inside or whether a quantum bounce replaced it. The black hole can keep that secret. There is a useful difference here between a clock and a signal. Suppose a clock falls toward the black hole. The distant observer cannot simply compare its face continuously forever. They rely on light sent from the clock. That light has to climb outward through the curved space-time. As the emitter approaches the horizon, the received light is increasingly redshifted and delayed. So when we describe the distant observer seeing the infalling process slow down, we are partly describing how information from the process reaches them. The infalling clock itself has not become locally defective. This matters when we return to the bounce. The distant observer is not watching the compressed core in slow motion through a transparent horizon. There is no view of the Planck star gradually squeezing itself for billions of years. Once the relevant matter lies behind the event horizon, ordinary outgoing signals from it do not reach the exterior. The external delay concerns the global geometry and the relationship between the interior transition and when its effects could become externally accessible. We should therefore avoid picturing a giant cosmic security camera aimed through the horizon, with the playback speed set to 0.0000000000001. There is no such camera. The interior is causally hidden. For the bounce to affect the outside universe later, the geometry itself must evolve beyond the ordinary classical black hole configuration. That takes us back to the proposed white hole phase. Inside the quantum region, contraction has become expansion. But expansion alone cannot carry matter through an unchanged event horizon. The causal structure needs to change. In black-to-white hole models, quantum gravity provides the transition. What was previously an inward trapping geometry eventually connects to an outward emerging geometry. Now imagine the two clocks again, but do not try to keep them synchronized. The internal clock accompanies the collapse and bounce. The distant clock accompanies the black hole's long external history. The black hole may sit in a galaxy while stars orbit around it. The galaxy may evolve, other stars may be born and die. The black hole may accrete matter. It may merge with another black hole. Over immense timescales, Hawking radiation may become increasingly important. All of that can belong to the external story, while the local quantum transition occupies a radically shorter interval along the internal history. This is one of the reasons black holes are so difficult to discuss using ordinary language. We keep using phrases such as "at the same time." Relativity keeps asking us to specify what we mean. There is another tempting mistake. You might imagine that an observer falling into the black hole would therefore see the entire future of the universe rushing past before crossing the horizon. That is not generally correct. The distant universe can appear distorted, blue-shifted, and temporally altered depending on the observer's motion and the geometry. But falling through an event horizon does not automatically provide a convenient screening of all events until the end of cosmic history. The idea that you casually watch eternity pass outside before crossing is an oversimplification. The relationship among emitted signals, received signals, horizons, and proper time has to be calculated for the specific space-time. Black holes are strange enough without giving them abilities they have not requested. What matters is that two world lines can accumulate radically different amounts of proper time. And around black holes, the difference can become extreme. The Planck star proposal takes advantage of exactly that. The quantum bounce does not need to sit at the centre, slowly carrying out its work for the entire external lifetime. Locally, the transition can be short. Externally, the resulting change can remain inaccessible for a very long time. The original proposal described this as a Planck star living for a short time in its own frame while appearing enormously long-lived from outside. Now this creates a very interesting observational possibility. Suppose the external waiting period is not infinite. Suppose, after an enormous but finite time, the black hole geometry really does transition into an expanding or white hole-like phase. The stored energy and information that had been hidden behind the horizon would no longer be hidden in the same way. Something could emerge. What would that look like? The answer depends heavily on the model and on the mass of the black hole. A large black hole and a small black hole do not have the same characteristic timescales. Smaller black holes have stronger Hawking emission and shorter Hawking lifetimes. If primordial black holes formed in the early universe with suitable masses, some theoretical scenarios have considered whether they might reach a quantum gravity transition during the present cosmic era. That possibility is one reason Planck star models have occasionally been connected with searches for unusual astrophysical transients. Perhaps some compact objects formed when the universe was young. Perhaps they spent nearly the entire age of the cosmos looking like black holes. Inside, the relevant quantum process could occupy only a modest proper time. Outside, billions of years could pass. Then, at some point in cosmic history, the exterior geometry could finally reflect what the interior had already done. This is where the phrase, "a tiny moment that lasts for ages," becomes more than a dramatic description. One process can be associated with very different durations along different parts of space-time. The short interval belongs to the deep quantum history of the collapsing matter. The long interval belongs to the external black hole history. They are not two competing answers to the same clock-reading question. They are measurements made along different physical histories. General relativity already allows that. Quantum gravity is being asked to describe how those histories connect through the bounce. And there is no need for the matter to spend the entire external lifetime crushed at exactly one fixed density. This is another place where everyday intuition can get in the way. We imagine a Planck star as a dense ball sitting inside the black hole for trillions of years, like a very compact tenant waiting for the lease to expire. But the interior geometry need not correspond to that simple picture. The quantum bounce describes an evolution of matter and geometry. The relationship between that interior evolution and external Schwarzschild-like time is highly distorted. Trying to picture both using one ordinary sequence of snapshots can be misleading. A space-time diagram is often more useful. Instead of imagining the universe as three-dimensional space changing according to one universal clock, imagine the full history as a four-dimensional structure. The collapsing star traces one region of that structure. The horizon forms. The interior quantum region occupies another. The distant observer follows a world line far outside. The later transition occupies yet another part. Different clocks measure the lengths of different paths through that geometry. Suddenly, asking how a brief bounce and a long-lived black hole can coexist becomes less mysterious. They belong to different paths. Of course, this only explains how the timing could be consistent. It does not prove the bounce occurs. General relativity gives us time dilation. Quantum field theory gives us strong reasons to take black hole thermodynamics seriously. The Planck star bounce and black-to-white hole transition remain proposals about physics we have not directly observed. The timing mechanism makes the proposal possible. Evidence would have to tell us whether nature actually uses it, and that returns us to the outside universe. For most of its existence, a black hole containing a hypothetical Planck star might look frustratingly ordinary, dark, compact, massive, surrounded perhaps by hot gas, perhaps by nothing at all. Its exterior can resemble the black hole's general relativity already describes. The interesting event comes later. If the external delay eventually ends, the distinction between hidden interior and observable exterior changes. The bounce that occupied a tiny interval in the deep interior may finally have an external consequence. Matter, radiation, or quantum information may emerge through a white hole-like phase. Energy that had been trapped behind a black hole horizon may become accessible again, and because the black hole could have spent an enormous amount of external time reaching that stage, the event might occur long after anyone who watched the original star collapse had disappeared. A star dies. A black hole forms. The galaxy changes. Ages pass. The long external wait brings us to the most uncertain part of the Planck star idea. Suppose the collapse really did bounce deep inside the black hole. Suppose quantum gravity prevented the singularity from forming. Suppose the matter that once made the star never reached an infinitely dense endpoint, but instead passed through a very dense quantum state and began expanding again. For an observer falling with that matter, the important change may have happened long ago according to their own local clock. For the distant universe, however, the object has continued to behave like a black hole. It has remained dark. It may have orbited through a galaxy for billions of years. Gas may have fallen around it. Stars may have passed nearby. Other black holes may have merged with it. The universe outside may have changed enormously, while the deep interior followed a very different timetable. Eventually, though, a model that includes a bounce has to answer a practical question. What becomes of the expanding matter? A bounce is not enough by itself. Inside an ordinary classical black hole, expansion does not provide an escape route through the horizon. The horizon is not a material shell that can be broken from the inside. It is part of the causal structure of space-time, so the expanding region cannot simply fly outward through an unchanged black hole. Something more fundamental has to happen. The geometry itself has to change. This is where the white hole enters. A white hole is not an object astronomers have found and placed in a catalogue. We have no confirmed observation of one. It appears first as a possibility within the mathematics of general relativity. In a simplified sense, a white hole behaves like the time reverse of a black hole. Matter can enter a black hole but cannot come back out through the horizon. For a white hole, matter can emerge from the corresponding region, while ordinary future-directed paths from outside do not simply cross inward in the same way. That sounds strange because we're used to black holes being described as one-way doors. A white hole points the one-way behavior in the opposite direction. This does not mean a black hole can be converted into a white hole using classical general relativity whenever it becomes bored with being black. Classically, once gravitational collapse forms a black hole, the ordinary equations do not provide a simple later stage where the horizon reverses and everything comes back out. The proposed transition requires quantum gravity. In some Planck star-related models, The bounce in the deep interior is connected with a later change in the larger space-time geometry. The collapsing black hole phase is followed by an expanding white hole phase. Rather than ending at a singularity, the history continues. That is the basic idea. It is also where the phrase "the Planck star reappears" needs some care. Nothing has been sitting visibly behind a curtain waiting to step back onto the stage. The external observer never had direct access to the quantum core. During the black hole phase, the horizon prevented ordinary signals from that region from reaching the outside. If a later transition produces a white hole-like geometry, the causal structure changes. The region that was hidden can become connected to the outside in a new way. Matter, radiation, or information associated with the previous interior may then be able to emerge. That is very different from an object simply climbing back through the same event horizon it crossed earlier. Imagine closing a road because every lane has been redirected toward a tunnel. Driving faster does not help you leave because there is no outward lane. A black to white transition is not a car finding enough power to drive against the traffic. It is the road network itself being rebuilt. The directions available through space-time change. This is why the proposal can avoid requiring matter to move faster than light. The matter does not defeat the causal structure of the black hole. The causal structure is no longer the same. Haggard and Ravelli constructed a model in which space-time remains classical outside a finite quantum region, while a black hole undergoes a quantum transition into a white hole. In that kind of picture, quantum effects do not need to dominate the entire exterior for the entire lifetime of the object. They become decisive in the region where classical evolution cannot provide the complete history. Later models have tried to make that geometry more explicit. Researchers have constructed non-singular spacetimes where collapsing matter forms a black hole region, encounters a quantum-corrected interior, and later expands through a white hole region in the same asymptotic universe. That last part matters. Some older mathematical extensions of black hole solutions lead to additional regions that are difficult to interpret as the future of an ordinary star collapsing in our universe. A useful model of stellar collapse should instead explain what happens to one object in one external universe. A star collapses here. A black hole forms here. If a white hole phase follows, the material eventually reappears here as well. That is much closer to the physical question the Planck star proposal is trying to address. Now, picture the external black hole late in its life. For most of its history, it may have been large compared with the deep quantum region. The horizon hid what happened inside. Hawking radiation slowly reduced the black hole's mass. The horizon became smaller. The exterior remained approximately classical over scales where quantum gravity was negligible. Eventually, the object enters a regime where the semi-classical picture becomes increasingly difficult to trust. At that point, different theoretical models begin to disagree more strongly. One possibility is that the black hole undergoes a transition into a white hole before reaching the final endpoint expected from a purely semi-classical evaporation calculation. Another possibility is that evaporation continues until a very small remnant remains, and that remnant has white hole-like properties. Another model may leave a stable remnant without an observable explosive re-expansion. There is no confirmed answer. Even within research inspired by loop quantum gravity, the exact fate of an evaporating black hole remains under investigation. So when we ask what happens when a Planck star finally reappears, we are choosing one proposed branch of the story. In that branch, the black hole state does not remain permanent. At some stage, quantum gravity allows the trapping structure to change. The black hole horizon gives way to a white hole-like region. The system that had been compressed and hidden now has an outward future. What comes out? The safest answer is that we do not yet know in sufficient detail. The original matter cannot be expected to emerge looking exactly as it did before collapse. A star is not likely to disappear into a black hole and return billions of years later with its photosphere restored, its fusion reactions restarted, and a mild complaint about the delay. The collapse was violent. The matter entered densities where ordinary atomic and nuclear structures ceased to be meaningful. It passed through an environment where quantum gravity may dominate. Any material emerging from such a process would have undergone extreme transformation. Energy could come out as particles and radiation. Quantum information associated with the earlier collapsing state could, in principle, be carried by the outgoing state. The exact spectrum would depend on the model. That makes the word explosion tempting. Some early work on Planck star phenomenology discussed the final event in terms of an explosive release. If a primordial black hole underwent a transition after a long external lifetime, the event might produce a burst that could in principle be searched for astronomically, but we should not imagine a conventional stellar explosion. A supernova occurs when a star's internal structure changes and enormous energy drives its outer layers into space. A black-to-white hole transition would involve a change in space-time geometry associated with quantum gravity. There is no ordinary stellar surface. There is no envelope waiting above a collapsing iron core. The mechanism is fundamentally different. Even the energy available to an outside observer requires care. A black hole may originally have formed with a large mass. During a long lifetime, Hawking radiation can carry away some or most of that mass energy. If the transition occurs only after substantial evaporation, the object at the time of the final white hole phase may have far less mass than the original black hole. That means the final event is not necessarily the entire original star suddenly returning in one gigantic release. Some energy may already have left through Hawking radiation over the preceding history. Some information may be associated with the outgoing radiation. Some may remain in the late quantum geometry. How these pieces fit together depends on the specific model. This is important because the phrase Planck star explosion can make the proposal sound more definite than it is. There is no single agreed Planck star explosion profile. There is no confirmed prediction that says such an event must produce one exact burst duration, one wavelength or one amount of energy. Different assumptions about the black hole lifetime, bounce geometry, mass, surrounding environment, and final quantum state lead to different observational possibilities. Earlier proposals examine primordial black holes because their masses could make the timescales more interesting. A primordial black hole would not have formed from the collapse of an ordinary star. It could have formed from extreme density fluctuations in the early universe. Depending on its initial mass, such a black hole could be much smaller than the black holes made by stars. Smaller black holes are important because many relevant timescales depend strongly on mass. They are hotter in Hawking's description. They evaporate faster. And in some black-to-white hole scenarios, lower mass objects could reach the transition during an era when astronomers might actually be around to notice. That led to suggestions that unusual short bursts of radiation might carry evidence of a quantum gravity transition. At one stage, fast radio bursts were discussed as a possible comparison. Fast radio bursts are brief, intense radio signals arriving from cosmological distances. When some Planck star phenomenology was first developed, their origin was still largely mysterious, which naturally made them attractive to theorists with unusual compact object models. Since then, astronomers have connected at least some fast radio bursts strongly with magnetars, highly magnetized neutron stars. So it would be a mistake to say that fast radio bursts are evidence for Planck stars. They are not. The historical suggestion remains useful for another reason. It demonstrates how a theory this remote from laboratory experiments could become testable. You begin with a quantum gravity model. The model predicts a possible black hole transition. You calculate a timescale that determines what masses might undergo the transition today. The mass and geometry then influence the characteristic energy or wavelength of any emission. Astronomers search the sky. If no events with the predicted properties appear, portions of the model can be constrained. If an unusual signal appears, researchers ask whether ordinary astrophysical explanations can account for it, before announcing quantum gravity. That final step is especially important. The universe contains many ways to produce dramatic bursts. Neutron star mergers, magnetoflares, supernovae, black hole accretion events, tidal disruption events, relativistic jets, compact object collisions. A strange flash in the sky does not become evidence for a white hole merely by being strange. A convincing detection would require distinctive predictions that separate the quantum gravity model from more conventional sources. Still, the idea of a white hole transition gives us something that the singular classical picture does not provide: a future. In classical gravitational collapse, the interior evolution reaches the singular boundary. The space-time description becomes incomplete. In the bounce picture, the history continues through the high-density region. If the expanding branch eventually becomes a white hole geometry, the system has an outward continuation. That has consequences for the information problem we discussed earlier. The black hole may not need to destroy the information associated with everything that fell inside. The information could remain encoded through the quantum transition. When an outward phase becomes accessible, some or all of that information may return to the external universe. Again, it would not come out in a convenient form. Imagine dropping a novel into a black hole. If information is preserved and later released, nobody should expect the white hole to print a fresh copy and politely return it. The quantum state of the outgoing radiation may contain correlations ultimately related to the original state. Reconstructing the book from those correlations could be so difficult that no realistic observer could do it. Fundamental preservation and practical recoverability are very different things. Your laptop can preserve a file perfectly. A black hole may have a less user-friendly interface. There is another version of the white hole idea where the final phase is not a violent brief event at all. Some models investigate long-lived white hole remnants. The original black hole evaporates. Its external mass becomes small, but the internal geometry may still contain a large interior associated with the earlier black hole. The remaining object could then persist as a small quantum remnant. From outside, it might have very little mass and a tiny characteristic scale. Internally, it could retain information accumulated during the black hole phase. This sounds impossible only if we assume that the inside of a black hole must have the ordinary geometry of a ball in flat space. It does not. In general relativity, interior spatial volume and exterior horizon size do not have the simple relationship that an ordinary container has. A small opening does not necessarily imply a small interior geometry. Researchers have therefore explored whether a late white hole remnant could be small outside, large inside, and long-lived. Such remnants have even been proposed as possible dark matter candidates. That is another speculative step. There is no evidence that dark matter is made of white hole remnants. There is not even agreement that such remnants form. Recent theoretical work continues to produce different possible end states. One 2025 loop quantum gravity analysis of Hawking evaporation found evidence within its particular effective framework favouring a black to white hole transition rather than a stable remnant. Other recent work has explored stable Planck star remnants whose bounce remains causally hidden rather than producing an observable re-expansion. So even the phrase, "what happens when it reappears," contains a scientific assumption. Maybe it reappears in an outward white hole phase. Maybe a small remnant remains. Maybe the correct theory of quantum gravity gives us a different answer entirely. That uncertainty should remain in the story because it tells us exactly where the frontier is. The established physics takes us through stellar collapse, black hole formation, relativistic horizons, and the semi-classical prediction of Hawking radiation. The singularity indicates that the classical description cannot be the whole story. Quantum gravity models then attempt to complete the evolution. The Planck star scenario replaces the singular endpoint with a finite density quantum region and a bounce. The black to white hole scenario asks whether that bounce can eventually change the causal structure enough for an expanding phase to emerge. Every step after the established black hole description brings more theoretical uncertainty. That does not make the idea meaningless. It makes the predictions more valuable. A theory that claims something unusual happens to black holes eventually has to tell us what an astronomer should look for. If a white hole transition releases particles, what energy should they have? If the event produces electromagnetic radiation, what wavelengths should dominate? How long should the burst last? How often should such events occur? Would they be concentrated at cosmological distances? Could primordial black holes produce them? Could there be a population of remnants left behind? Would those remnants affect dark matter, gravitational lensing, cosmic backgrounds, or gravitational wave observations? Those questions move the Planck star from the inaccessible interior of a black hole toward observations, and that is a difficult transition in its own right. Inside the black hole, theorists can construct models that replace a singularity with quantum geometry. Outside, nature has to provide evidence. A white hole would not receive a label when it appeared. A telescope would record photons, particles, or perhaps gravitational effects. Astronomers would have to work backward from those measurements. They would compare the signal with known astrophysical sources. They would test competing models. Most unusual events would probably turn out to have ordinary explanations. That is how astronomy normally works. The sky surprises us. Then we spend years making the surprise less mysterious. For a Planck star, however, one possibility is unusually appealing. A tiny black hole formed in the early universe could spend almost the entire history of the cosmos in a black hole phase. Its internal bounce could occupy a much shorter local interval. Only after the enormous external delay would the geometry complete its transition. If such an object changed into a white hole-like phase now, the radiation reaching a telescope could be the final visible consequence of a collapse that began billions of years before Earth existed. The event would appear sudden. Its history would not be sudden at all. It would contain the formation of the black hole, the hidden quantum bounce, the long external delay, evaporation or other evolution, and finally the change that allows the interior state to communicate with the outside again. No single observer needs to watch the entire process. The universe does the waiting. The detector only sees the part that arrives at the end. That brings us to a much more practical problem. Suppose one of these transitions happens somewhere in the observable universe. So now the problem becomes embarrassingly practical. Suppose Planck stars exist. Suppose black holes really can avoid singularities through quantum gravitational bounces. Suppose some of them eventually undergo black to white hole transitions and release something back into the universe. How would we know? A telescope cannot point toward an event and display a message saying, "Quantum gravity detected." Astronomers receive light, particles, gravitational waves, and other measurable signals. From those signals, they have to reconstruct what happened. That is already difficult with ordinary astrophysics. A sudden burst of gamma rays might come from a merging pair of neutron stars. A powerful radio pulse might come from a magnetaire. An X-ray flare could come from matter being heated around a black hole. A gravitational wave signal might come from two compact objects merging billions of light years away. The universe has an impressive collection of ways to produce sudden flashes. Adding a hypothetical white hole transition to the list does not make the detective work easier. As of today, there is no confirmed observation of a Planck star, a black to white hole transition, or an astrophysical white hole. Everything we have discussed about detecting one begins with theoretical models. Researchers calculate what a possible transition might produce, then ask whether astronomical instruments could see something similar. That is exactly how an untested idea should approach observation. The difficulty is finding a signal distinctive enough that an ordinary astrophysical explanation would not immediately work just as well. Consider the most obvious possibility: a burst of light. If a hidden quantum core eventually becomes connected with the external universe, energy may be released over a relatively short period. Depending on the model, some of that energy could emerge as electromagnetic radiation. That gives astronomers several places to look: radio waves, microwaves, infrared radiation, visible light, X-rays, gamma rays. The electromagnetic spectrum gives you a large menu. Unfortunately, the universe has already ordered almost everything on it. Radio telescopes regularly find pulsars, active galaxies, jets, stellar flares, and fast radio bursts. Gamma-ray telescopes observe supernova-related events, neutron star mergers, active galactic nuclei, and other violent sources. So simply detecting a short, bright burst would tell us very little. The useful prediction has to be more specific. How energetic is it? What wavelengths dominate? How long does it last? Does it repeat? How does its observed wavelength change with distance? Does another signal arrive at the same time? Where in the sky does it appear? How often should these events occur? The Planck star proposal has produced some interesting answers to those questions, although the answers depend strongly on assumptions about the lifetime of the black hole and the nature of the final transition. One early line of work focused on primordial black holes. These are hypothetical black holes that could have formed in the early universe rather than from dying stars. The distinction is important. A black hole made by stellar collapse cannot have just any mass. The star has to provide enough material to form the black hole in the first place. Primordial black holes, in principle, could have formed across a much broader range of masses if regions of the early universe became sufficiently dense. Some could have been much lighter than the black holes we observe in stellar systems. And a smaller black hole is exactly what makes several potential Planck star signals more interesting. The proposed transition time depends on mass. The precise relationship differs among models, which is one of the large theoretical uncertainties. But in some versions of the black-to-white hole scenario, a black hole with a suitable substellar or roughly planetary scale mass could have a lifetime comparable to the age of the universe. That gives us an unusual possibility. A primordial black hole forms extremely early. Its internal collapse reaches the quantum regime. A bounce occurs after a short local interval. Externally, the object remains black hole-like for billions of years. Then, during the period in which humans happen to be building radio antennas and gamma-ray telescopes, the transition becomes observable. This would be unusually considerate behavior from quantum gravity. There is no guarantee that nature has arranged things so conveniently. Still, it gives us something to calculate. One proposed signal is a short burst with a wavelength connected to the size of the black hole at the transition. For the masses considered in some early Planck star models, that characteristic scale can reach the millimeter region rather than remaining anywhere near the actual Planck length. This is one of the stranger aspects of the proposal. The fundamental quantum gravity scale is absurdly small, around 10 to the minus 35 meters. Yet the enormous time and mass scales involved in black hole evolution can, in some models, amplify the observable consequences to wavelengths that astronomical instruments can actually measure. You would not be detecting a Planck-length photon. You would be observing a macroscopic consequence of physics that originated in a Planckian regime. Some models also predict a higher energy component. If primordial matter was trapped during the formation and internal evolution of the black hole, the final transition might release high-energy particles or photons. Earlier phenomenological studies considered gamma-ray emission, in some cases reaching very high energies. That creates the possibility of looking for short gamma-ray bursts with unusual properties. Again, the difficulty is identification. The term gamma-ray burst already refers to a well-established astronomical class. Some long gamma-ray bursts are connected with the deaths of massive stars. Short gamma-ray bursts are strongly associated with mergers involving neutron stars. We have observed gravitational waves from a neutron star merger together with electromagnetic radiation, giving a very convincing physical explanation for at least part of that population. A Planck star burst therefore could not be identified simply by arriving in gamma rays and being brief. It would need something else. One proposed clue is the relationship between wavelength and distance. Normally, radiation travelling through an expanding universe is cosmologically redshifted. light emitted by a distant source reaches us with a longer wavelength, because the universe expanded while the light was travelling. The farther away we look, generally speaking, the further back in cosmic history we are observing. Now add a population of primordial black holes whose transition lifetime depends on mass. A Planck star event seen very far away occurred earlier in cosmic history. If the lifetime depends on mass, the black hole capable of transitioning at that earlier time would have a different mass from one transitioning closer to us today. Its size at the transition could therefore be different. Its emitted characteristic wavelength could also be different. That means two effects act at once. Cosmic expansion stretches the wavelength. The changing mass of the black holes that are able to explode at different cosmic ages changes the wavelength they emit in the first place. Under certain Planck star models, these effects partially compensate one another. The predicted wavelength-distance relationship becomes flatter than the ordinary cosmological redshift relationship. That's much more interesting than simply predicting a burst. If astronomers observed a population of transient events whose characteristic frequencies changed with distance in the specific way predicted by the model, that would be difficult to dismiss as coincidence. It still would not immediately prove the existence of Planck stars. Astrophysicists are extremely reluctant to declare quantum gravity before checking whether a neutron star has found another creative way to cause trouble, but a distinctive frequency-distance pattern would provide something testable. Radio emission has also received attention. When early Planck star phenomenology was being developed, fast radio bursts were still one of the great new mysteries of astronomy. These events last only milliseconds or so, yet they can be extraordinarily bright at radio wavelengths. They arrive from distant galaxies. When first discovered, nobody knew what was producing them. Naturally, almost every compact object with a pulse entered the discussion. Neutron stars, black holes, cosmic strings, exotic particle physics, Planck stars. Theoretical physics saw an unexplained radio flash and responded exactly as you would expect. Everyone brought a theory. The situation is different now. Astronomers have accumulated thousands of fast radio bursts, including repeating sources. Some have been localized to their host galaxies. Most importantly, magnetas have become firmly connected with fast radio burst production. Magnetas are neutron stars with enormously strong magnetic fields. In 2020, a magneta in our own galaxy produced an intense radio burst similar to the extragalactic fast radio burst phenomenon. Later observations have given increasingly detailed evidence that at least some fast radio bursts originate in the highly magnetized environments around neutron stars. So fast radio bursts are not evidence for Planck stars. That does not logically prove that no radio burst could ever come from a black-to-white hole transition. Different physical sources can sometimes produce signals in the same wavelength range. But any Planck star explanation now faces a much higher standard. It would have to predict a subset of events with properties that magnetar models cannot explain. Perhaps the energy would be different. Perhaps the surrounding environment would be wrong for a neutron star. Perhaps the burst would be accompanied by a characteristic gamma-ray signal. Perhaps its relationship between distance and wavelength would follow the quantum gravity prediction. One mysterious flash is not enough. A pattern would be much more persuasive. There is another way to search. Do not wait for a final explosion. Look for the population that should produce the explosions. If primordial black holes are required for observable Planck star events today, then primordial black holes themselves become part of the test. Astronomers search for primordial black holes in several ways. They can look for gravitational lensing, where a compact object's gravity temporarily magnifies a background star. They can study how compact objects would affect stars, galaxies, and other astrophysical systems. They can search for Hawking radiation signatures from sufficiently small black holes. They can study gravitational wave merger populations. They can compare cosmological observations with models describing how primordial black holes would have formed and evolved. These searches place limits on how abundant primordial black holes can be at different masses. The limits are complicated. There is no single statement saying primordial black holes are either completely allowed or completely ruled out. Different mass ranges are constrained by different observations. Some ranges are tightly limited, others remain more open. A major review published in 2026 still describes primordial black holes as an active possibility that could constitute some, and in certain allowed scenarios potentially a substantial fraction, of dark matter, while emphasizing the broad network of observational constraints. So the Planck star search is partly connected to a larger question. Were primordial black holes ever common enough for us to expect their quantum transitions? If observations eventually rule out the relevant mass range at the abundance required by a particular Planck star model, that version of the model becomes much harder to maintain. Non-detection matters. Science does not require a telescope to photograph the hypothetical object before observations become useful. Sometimes the strongest result is realizing that something should have appeared hundreds of times and did not. Imagine a model predicts 10 bright bursts every year within a distance where our instruments would easily detect them. Astronomers operate for 20 years. No suitable events appear. The model now has a problem. Perhaps the event releases less energy than expected. Perhaps the relevant black holes are rarer. Perhaps the transition takes longer. Perhaps the entire mechanism is wrong. Each possibility can be tested further. That is how an exotic theoretical idea gradually becomes an observational science problem. There is also the possibility of a diffuse signal. Suppose Planck star transitions occur throughout cosmic history. Individual bursts may be too weak or too distant to identify one by one. But all of them together could contribute to a background of radiation. Astronomers already study cosmic backgrounds across many wavelengths. There is the cosmic microwave background. There are diffuse gamma-ray backgrounds. There are radio backgrounds. There are populations of unresolved sources contributing light that cannot initially be separated into individual objects. A population of Planck star transitions could, under some models, add a distinctive component. The integrated spectrum might carry information about the masses, formation history, and transition times of the primordial black hole population. This kind of search has one practical advantage. You do not have to be looking in exactly the right direction during a millisecond burst. You examine the accumulated radiation. The disadvantage is that many other sources contribute to cosmic backgrounds. Galaxies, active black holes, stars, cosmic rays interacting with matter and radiation, unresolved transient populations. You then have to identify a relatively small extra component inside a much larger astrophysical mixture. Astronomy frequently turns into the scientific version of hearing one person whisper during a crowded dinner. Gravitational waves provide another possible route into quantum black hole physics. LIGO, Virgo, and Cagra have transformed black holes from objects we mostly study through their influence on surrounding matter into objects whose dynamics we can directly measure through ripples in space-time. When two black holes merge, the final object settles down through a stage called ring-down. The gravitational wave signal during ring-down contains characteristic frequencies, determined largely by the mass and spin of the resulting black hole. This gives physicists a powerful test of general relativity. The clearest black hole merger signal available by 2025, GW250114, allowed unusually precise measurements of multiple ring-down modes. Those measurements agreed impressively well with the behavior expected for a classical black hole described by general relativity. That does not rule out a Planck star hidden deep inside. A model designed to reproduce an ordinary classical exterior may look exactly like a standard black hole in measurements of the exterior. In fact, it has to. If a proposed Planck star caused every observed black hole to ring completely differently from Einstein's prediction, gravitational wave data would already create serious trouble for the model. The interesting question is whether tiny deviations could appear. Some broader quantum gravity models predict late-time gravitational wave structures sometimes called echoes. The basic idea is that if the region near the would-be horizon differs from the classical expectation, part of the gravitational wave signal might be reflected and return after the main ringdown. You would hear the merger. Then, after a delay, a weaker repetition or modified signal might follow. There have been searches for such echoes. There have also been claims and counterclaims about possible evidence. At present, gravitational wave echoes are not an established detection of quantum structure, and they should not be presented as evidence for Planck stars. More importantly, echoes are not unique to the Planck star proposal. Many hypothetical compact objects or near-horizon modifications could produce related effects. So even a convincing echo would not automatically tell us that a Planck star was sitting inside the black hole. It would tell us that the classical description might need modification. Then the difficult work would begin. Still, gravitational wave astronomy is improving quickly. In 2015, humanity detected gravitational waves from a black hole merger for the first time. A decade later, the detector network had accumulated hundreds of black hole merger candidates, and the cleanest signals were allowing detailed tests of the final black hole's ringdown. Future detectors should be even more sensitive. Ground-based observatories such as the planned Einstein Telescope and Cosmic Explorer aim to observe black hole mergers with far greater reach and precision. The space-based LISA mission is designed to study gravitational waves at lower frequencies, including signals from much more massive black holes. Better measurements mean better opportunities to test whether horizons and ringdowns behave exactly as classical relativity predicts. That would not be a direct Planck star detector, but it could close or open parts of the theoretical landscape. There may also be a quieter signature, remnants. We have discussed the possibility that a black hole does not finish with a dramatic white hole explosion. Some models leave behind small, long-lived quantum objects. Recent theoretical work has explored whether Planck star or white hole remnants could contribute to dark matter. That possibility completely changes the detection strategy. Instead of searching for a flash, you search for an invisible population. Dark matter reveals itself primarily through gravity. We infer its presence because stars and galaxies move as though more mass exists than we can see. Gravitational lensing maps matter that does not emit ordinary light. Cosmological observations require additional gravitating matter beyond the familiar atoms making stars, planets, and people. If Planck star remnants were stable and sufficiently abundant, they could contribute to that missing mass. Again, there is currently no evidence showing that dark matter is made from Planck star remnants. The proposal simply gives us another way the theory could have observable consequences. A remnant population might produce gravitational lensing events. Its formation history might affect cosmology. Its mass distribution could be constrained by astronomical surveys. If the remnants interact in unusual ways, those interactions could provide further signatures. The details depend heavily on the model. Interestingly, not every recent Planck star remnant model predicts a visible bounce at all. Some work has examined scenarios where the collapse reaches a quantum bounce, but the bounce remains causally hidden from outside observers, leaving a compact remnant instead of a dramatic re-expansion. That's a reminder that Planck star does not refer to one universally agreed astrophysical prediction. The central idea is singularity avoidance through quantum gravity effects at extreme density. What happens afterward varies among models. That makes observation harder. A good prediction should ideally be difficult to change after the data arrive. If one version predicts a radio flash, another predicts gamma rays, another predicts a white hole remnant, and another predicts nothing directly visible, then seeing none of them does not immediately eliminate the broad idea. Physicists need models precise enough that observations can genuinely threaten them. Otherwise, the theory becomes very good at surviving and not very good at predicting. That is why identifying a smoking gun matters so much. A convincing Planck star detection would probably require several pieces fitting together. You might find a transient with an unusual spectrum. Its duration might match a predicted black-to-white hole transition. Its distance might correlate with its characteristic wavelength in the expected way. Its sky distribution might match a primordial black hole population. Perhaps a gamma-ray component and a radio component would appear together. Perhaps other wavelengths would be absent where ordinary astrophysical models predict they should be present. Then researchers would compare the event with magnetars, neutron star mergers, accreting black holes, and every other known source capable of producing similar signals. Only after those explanations repeatedly failed would quantum gravity begin looking like the less unreasonable option. One event would be exciting. A population would be much better. Suppose astronomers discovered 50 transient sources. Each had the same unusual spectral structure. Each showed the same relationship between distance and characteristic wavelength. None occurred in environments associated with young neutron stars. None behaved like known gamma-ray bursts. The event rate matched a plausible primordial black hole abundance, and a quantum gravity model had predicted those features before the observations were made. That would be far more convincing than discovering one strange flash and designing a Planck star explanation afterward. Prediction is the important part. Physicists would also want independent evidence. Perhaps gravitational lensing surveys had already revealed compact objects in the correct mass range. Perhaps cosmological constraints allowed the necessary primordial population. Perhaps gravitational wave observations showed small deviations compatible with the same quantum geometry. Perhaps a diffuse radiation background contained the integrated signature predicted by the transient population. Different instruments detecting different consequences of one model would make the case much stronger. This is called multi-messenger astronomy when different kinds of signals are combined. Light can tell us one thing, gravitational waves can tell us another. Neutrinos can provide another route. Cosmic rays can carry information about extremely energetic processes. A convincing quantum gravity event might eventually be recognized not because one telescope saw something spectacular, but because several detectors saw compatible pieces of the same event. There is no guarantee that Planck stars produce all of those messengers. That has to come from the physics. But astronomy has learned how powerful this approach can be. When two neutron stars merged in 2017, gravitational waves revealed the collision, while telescopes across the electromagnetic spectrum studied the resulting light. The combination provided much more information than either signal alone. A future exotic transient would receive the same treatment. The alert would go out. Radio observatories would turn. X-ray and gamma-ray satellites would check the sky. Optical telescopes would search for a counterpart. Gravitational wave teams would look through their data. Astronomers would identify a host galaxy if possible. The distance would be measured. The environment would be examined. And somewhere, a theorist who had been talking about white holes for 30 years would probably become extremely difficult to reach by telephone. But even extraordinarily good observations face one final obstacle. Planck stars are supposed to hide their most important physics behind a horizon for most of their existence. We cannot watch the quantum bounce directly. We are trying to infer it from whatever the system does later. That means several different interior models could potentially produce similar exterior signals. The singularity could be replaced by a Planck star, or another quantum gravity structure, or some entirely different non-singular geometry. A burst that demonstrates black hole decay would not necessarily demonstrate the exact microscopic mechanism. Physics often works this way. Astronomers knew the sun was powered by something for centuries before nuclear fusion provided the correct explanation. Gravitational waves were predicted long before detectors could measure them. Black holes were inferred through their gravitational effects before horizon-scale imaging became possible. An observation can establish that something happens before we understand every detail of how it happens. So perhaps the first evidence for Planck star-like physics would not arrive labelled as a Planck star. It might begin as a transient that refuses to fit existing categories, or an unexpected population of compact objects, or a deviation in a black hole signal, or an odd background spectrum. Researchers would spend years trying ordinary explanations. Most of those explanations might work, one might not. That is the point where an idea developed to solve a singularity problem inside theoretical equations could finally become connected to a measurement. For now, that connection has not been made. Our best black hole observations continue to agree extremely well with general relativity in the regions we can probe. The exceptionally clear GW250114 merger, for example, produced ring-down behavior consistent with the predictions for a classical black hole and allowed some of the strongest tests yet of Einstein's theory in the strong gravity regime. That is not bad news for Planck stars. A viable Planck star model is supposed to reproduce general relativity where quantum gravity corrections are negligible. The strange physics is hidden much deeper. The observational challenge is finding a situation where it can no longer remain hidden. Primordial black hole transitions may offer that possibility. Late white hole phases may offer another. Remnants could offer another. Future gravitational wave measurements may constrain the geometry more tightly. Radio and gamma ray surveys will continue finding vast numbers of transient events. Dark matter searches will continue narrowing the possible populations of unseen compact objects. Each observation reduces the room available for speculation, and that is useful even if no Planck star is ever detected. A theory of quantum gravity cannot remain protected forever by the fact that the Planck scale is difficult to reach. If the theory predicts macroscopic consequences, those consequences can be tested. If the predicted bursts do not exist, some models fail. If the required primordial black hole population is excluded, some models fail. If future measurements show black hole behavior incompatible with a proposed transition, that model fails. If every increasingly precise observation continues matching classical black hole expectations without the predicted deviations, the available possibilities become narrower. That is how an object hidden behind an event horizon can still become a scientific question rather than merely an imaginative one. We may never place a detector inside a black hole. We may never directly watch matter reach Planck density, but the universe can perform the experiment for us. The task is to find out whether it leaves anything behind that our instruments can recognize, and once we ask the question that way, detection is only half of the problem. Even if the searches remain silent, we still have to decide what the theory itself has earned the right to claim. Because after black holes, singularities, quantum geometry, bounces, white holes, billions of years of time dilation, hypothetical bursts and possible remnants, one question is still sitting underneath everything we have discussed. Do Planck stars really exist? We do not know. No Planck star has been observed. No astronomer has identified a white hole and traced it back to a quantum bounce inside a black hole. No detector has measured matter reaching Planck density inside a collapsing star. And no experiment has yet confirmed loop quantum gravity as the correct theory of quantum gravity. That does not mean the idea has been disproved. It means Planck stars still belong to theoretical physics rather than established astrophysics. There is an important difference between those two categories. Black holes were once theoretical objects too. Einstein's equations allowed them long before astronomers had strong observational evidence that nature actually made them. Neutron stars were predicted before pulsars revealed that extraordinarily dense stellar remnants were really out there. Gravitational waves spent roughly a century as a prediction before instruments finally measured them directly, so being theoretical is not a criticism. Every new physical idea begins there. The question is what happens next. Does the theory remain internally consistent? Does it solve a real problem? Does it reproduce the physics we already know works? Does it make predictions that differ from competing explanations? And eventually, does nature agree? Planck stars have a reason for being proposed in the first place. They are not an attempt to make black holes more interesting. Black holes have managed that without assistance. The idea begins with an actual problem in classical general relativity. Follow gravitational collapse far enough, and the classical theory leads towards singular behavior. General relativity describes the formation of the black hole extremely well. It describes the exterior geometry. It predicts the horizon. It predicts how matter moves around the black hole. It predicts gravitational waves from merging black holes with remarkable accuracy. But deep inside, the classical evolution reaches a regime where the theory no longer provides a complete physical continuation. That is where physicists expect quantum gravity to become important. And that expectation is not unique to loop quantum gravity. Almost everyone working on the foundations of gravity agrees that general relativity and quantum physics cannot remain entirely separate in arbitrarily extreme conditions. Where researchers disagree is over what the correct quantum theory looks like. String theory offers one family of ideas. Loop quantum gravity offers another. There are causal set approaches, asymptotic safety programs, spin foams, group field theories, emergent space-time ideas, and several other directions. They do not all agree about what replaces a classical singularity. Some suggest that singularities disappear. Some replace them with quantum regions. Some change what we mean by space-time at very small scales. Some produce new phases of geometry. Some lead to descriptions so unlike an ordinary object that asking what sits at the centre may turn out to be the wrong question entirely. The Planck star is one answer within that larger uncertainty. Its attraction is easy to understand. We have seen gravity encounter forms of resistance before. A normal star resists collapse through pressure associated with hot matter and nuclear processes. A white dwarf can be supported by electron degeneracy pressure. A neutron star is supported by quantum effects and strong interactions in matter, compressed to nuclear densities. If gravity overwhelms all of those forms of support, classical relativity says the collapse continues. The Planck star proposal asks whether quantum gravity itself provides the next change in behaviour. At extreme density, the classical geometry would no longer be valid. Quantum gravitational effects would prevent unlimited compression. The collapsing material would reach a finite high-density state. Then it could bounce. There is a satisfying logic to that sequence, but satisfying logic is not evidence. Nature has no requirement to choose the solution we find elegant. This is where discussions of Planck stars sometimes become too confident. You might hear the idea described as though loop quantum gravity has already demonstrated what exists inside real astrophysical black holes. That is stronger than the science supports. Loop quantum gravity contains important mathematical results concerning quantum geometry. Related models have shown how singular behaviour can be replaced by bounces in simplified cosmological systems and black hole constructions. Researchers have developed increasingly sophisticated non-singular black hole models. But moving from those results to the statement, real black holes contain Planck stars, requires several additional steps. The first question is whether loop quantum gravity itself is the correct description of gravity at the quantum level. We do not yet know. General relativity has been tested repeatedly. Quantum mechanics has been tested repeatedly. The standard model of particle physics has survived an extraordinary range of experiments. Quantum gravity is different because the regime where its distinctive effects are expected to become large is extraordinarily difficult to access. We cannot build a laboratory black hole and inspect its core. We cannot directly probe distances near the Planck length using current accelerators. The energy required to investigate those scales in a straightforward way lies far beyond present technology. That forces quantum gravity research to proceed through mathematics, consistency conditions, indirect effects, cosmology, black holes, and any possible observable consequences that become amplified to larger scales. Then there is a second problem. Even if loop quantum gravity captures important features of nature, it does not automatically follow that the specific Planck star model is the unique outcome of stellar collapse. There are multiple ways of constructing quantum-corrected black holes within loop-based approaches. Different choices can produce different internal structures. Some models contain bounces, some produce black-to-white hole transitions, some suggest long-lived remnants. Some recent work has explored geometries where the bounce remains hidden and no dramatic re-expansion becomes visible from outside. Other work has found, within particular effective frameworks, evidence favouring a transition from black hole behaviour to white hole behaviour during the late evolution. Those possibilities are not minor variations. They change what an astronomer should expect to see. One model may predict a transient burst, another may leave an effectively invisible remnant, another may change the late stages of Hawking evaporation. If the underlying theory has not yet selected one unique observable outcome, then testing the broad idea becomes harder. This is normal for a developing field. The earliest models are often simplified. Researchers discover problems, assumptions are changed, better mathematical tools become available, previous conclusions are revised. The story becomes less tidy and usually more realistic. Planck stars have gone through exactly this kind of development. The original proposal in 2014 emphasized a finite density quantum core, a bounce, enormous external time dilation, and the possibility that an object emerging late in black hole evaporation could preserve information about the original collapse. That was a starting point. The following years brought black to white hole models, remnant scenarios, questions about stability, lifetime calculations, information storage, and attempts to connect the theory with astrophysical observations. That process continues. In 2025, for example, one effective loop quantum gravity study of Hawking evaporation found evidence within its model pointing toward a black-to-white hole transition rather than a stable final remnant. Another 2025 proposal explored Planck star remnants, in which a non-singular bounce occurs but remains causally hidden from external observers, leaving a stable object rather than an observable re-expansion. Two papers can therefore begin with broadly similar motivation and reach different predictions for the final state. That tells us something useful. The existence of quantum corrections does not automatically tell us what the completed black hole history must look like. We still have work to do. The third problem is observation. Suppose tomorrow an observatory detects an unusual burst. It lasts a fraction of a second. It comes from billions of light years away. Its spectrum looks unfamiliar. Would that prove Planck stars exist? Not remotely. Astronomers would first ask whether known astrophysics could explain it. A magneta flare, a neutron star merger, an unusual accretion event, a relativistic jet, a stellar explosion, a compact object collision, perhaps an instrumental error. Perhaps two unrelated signals arriving close together. Extraordinary explanations arrive late in the process, not early. This is why the possible signals we discussed matter only if the model predicts something distinctive. A particular relationship between characteristic wavelength and distance could help. A specific combination of radio and high-energy emission could help. A predicted event rate tied to a constrained primordial black hole population could help. A gravitational signature consistent with the same underlying model could help. One strange flash is interesting. A repeated pattern matching a prediction made in advance is science beginning to become persuasive. So far, that pattern has not appeared. Fast radio bursts once looked tempting because their origin was deeply mysterious. Now we know that at least some fast radio bursts are produced in neutron star environments, including magnetars. That does not mathematically prove no fast radio burst could ever have another origin, but it removes much of the motivation for using the mere existence of radio bursts as evidence for Planck stars. The unexplained became partly explained. That is what should happen. A speculative theory does not own every phenomenon that has not yet been understood. Then there are primordial black holes. Many Planck star detection scenarios rely on them, because ordinary stellar black holes are so massive and long-lived. Primordial black holes could, in principle, have formed with much lower masses in the early universe. Suitable masses could make quantum gravity transition timescales relevant to the current cosmic era in some models. But primordial black holes themselves have not been definitively detected. Observations constrain how common they can be across many mass ranges. Microlensing surveys, cosmic backgrounds, gravitational waves, stellar dynamics. Hawking radiation searches and other methods have steadily reduced the available parameter space. There are still allowed possibilities, but any Planck star model relying on a particular primordial population has to survive those constraints. That can be frustrating for the theory. It is excellent for science. Every independent observation forces the story to become more precise. Could enough primordial black holes have formed? Could they survive until the relevant transition time? Would their evaporation produce radiation we should already have seen? Would their gravitational effects disturb other systems? Could a population of remnants contribute to dark matter without violating observational limits? Each question gives nature another opportunity to say no, and a theory that survives repeated opportunities to fail becomes more interesting. There is an appealing temptation at this point to say that future telescopes will settle everything. Probably not quite. Even extremely precise observations may struggle to distinguish between different models of a black hole interior if all of them reproduce the same exterior geometry. Remember where the proposed Planck star spends most of its existence, behind the horizon. That is a remarkably effective hiding place. If quantum gravity corrections become important only deep inside while the exterior remains almost exactly described by general relativity, then ordinary measurements of stars orbiting a black hole will not reveal the difference. The black hole's mass can be the same, its spin can be the same, its horizon scale appearance can be the same, its gravitational influence can be the same. Even the gravitational waves from a merger may look essentially classical if the quantum structure remains hidden in a region that does not significantly affect the waveform. That is not a flaw in the model, it is partly the point. Quantum gravity should not destroy the successful predictions of general relativity where general relativity works, but it creates an observational challenge. The theory may differ from Einstein most strongly exactly where information cannot easily reach us. That leaves late-time transitions, evaporation, remnants, cosmology, and subtle gravitational effects as possible windows. Future gravitational wave detectors could help. Better measurements of black hole ringdown could test the geometry around newly formed black holes with greater precision. Space-based detectors will study massive black hole systems in regimes current instruments cannot reach. Large populations of mergers may reveal statistical patterns that individual events hide. None of that guarantees a Planck star discovery, but each improvement makes certain deviations harder to hide. High energy and radio astronomy will also continue improving. Transient surveys are becoming faster. More of the sky is monitored continuously. Events can be localized more accurately. Distances can be measured more reliably. When a strange burst occurs, several observatories can study it at once. A proposed black-to-white hole transition would eventually have to survive comparison with that growing database. There is another possibility that sounds much less exciting than an explosion, but may be just as important. Perhaps Planck stars exist and never produce dramatic visible events. Perhaps the quantum bounce remains hidden. Perhaps black hole evaporation leaves small stable remnants. Those remnants could be extremely difficult to detect directly. Some recent work has even explored whether such objects could contribute to dark matter. That idea is interesting because dark matter is itself inferred largely through gravity. A population of compact quantum remnants might be almost completely dark electromagnetically while still contributing mass. But now two unknowns have been placed together. We do not know that Planck star remnants exist. We do not know what dark matter is. Proposing that one unknown explains another can be scientifically useful if it produces testable predictions. It is not evidence by itself. A good dark matter candidate has to reproduce cosmological structure, satisfy gravitational constraints, survive lensing limits, behave correctly over cosmic history, and avoid producing signals that observations exclude. One 2025 study proposed a possible Planck star remnant dark matter scenario. Later work examining one formation mechanism found that LIGO limits on the gravitational wave background ruled out that particular route under Gaussian primordial initial conditions. leaving more restricted possibilities involving non-Gaussian formation. That is a perfect example of how theoretical physics is supposed to interact with observation. A proposal is made, an independent observation constrains it. The allowed scenario becomes narrower. No drama required. No declaration that the entire idea has been proven or destroyed. Just fewer places left for the hypothesis to hide. This leads to a useful way of answering our original question. Do Planck stars exist? There are 3 separate answers hiding inside that sentence. First, does classical general relativity leave us with a genuine reason to expect new physics inside black holes? Yes. The singularity problem strongly suggests that the classical theory is incomplete in the extreme interior. That does not prove any particular replacement, but the problem is real. Second, is it reasonable that quantum gravity could modify collapse before an infinite density classical endpoint is reached? Yes, that is a serious possibility. Many quantum gravity approaches investigate some form of singularity resolution. There are good theoretical reasons to think that extrapolating classical space-time indefinitely into the Planck regime is unsafe. Third, does nature specifically produce the objects in evolution described by Planck star models? We do not know. That is the crucial boundary. Everything before it motivates the idea. Nothing before it proves the idea. It is possible that future quantum gravity theory will show that the central intuition was correct, but the details were wrong. Perhaps collapse is stopped at finite density, but there is no white hole. Perhaps there is a bounce, but the exterior consequences differ completely from early models. Perhaps the correct theory contains a non-singular core with no object we would naturally call a star. Perhaps information is preserved through a mechanism unrelated to a long-lived Planck core. Perhaps the word inside itself becomes misleading when space-time is treated fully quantum mechanically. Or perhaps something very close to the Planck star picture survives. Physics has a habit of keeping the broad insight while replacing the first mental image. Atoms exist, but they do not look like tiny solar systems. Quantum particles exist, but they do not behave like microscopic billiard balls. Black holes exist, but they are not simply holes punched into an otherwise ordinary space. A future quantum description of their interiors may turn out to be equally difficult to visualize. That is why the word star should not distract us too much. A Planck star, if the idea is approximately right, would not be another species of star alongside red dwarfs, white dwarfs, and neutron stars. It would represent a quantum gravitational state reached after ordinary stellar structure has already disappeared. No hydrogen fusion, no shining surface, no familiar material held up by an ordinary pressure gradient. The name survives because the object comes from gravitational collapse, and because the proposed quantum effects resist further compression. What matters is the physics behind the name: finite density instead of a singular endpoint. Quantum geometry instead of purely classical spacetime, a continuing evolution instead of a world line simply terminating, possibly a bounce, possibly a white hole phase, possibly a remnant, possibly an observable signature. Each possibly is doing important work. And that uncertainty is not a weakness we need to hide. It is the honest state of the subject. There are areas of science where the basic picture is well established, and the remaining questions involve finer details. Planck stars are not there yet. They sit much closer to the boundary between what we know and what we're trying to construct. That makes them useful. A good speculative idea gives us a way to organize difficult questions. What replaces a singularity? Can quantum geometry resist collapse? How is information preserved? What is the final state of an evaporating black hole? Can an interior bounce influence the external universe? Are white hole geometries physically realizable? Can primordial black holes act as laboratories for quantum gravity? Could remnants survive? Could any of these ideas produce a measurable signal? Even if the final answer is that Planck stars do not exist, working through those questions can still teach us what a successful quantum theory of gravity must accomplish. It must explain why general relativity works at large scales. It must handle the extreme curvature of black hole interiors. It should not create arbitrary violations of causality. It has to fit quantum mechanics consistently. It has to say something sensible about information, and ideally it should produce consequences that can be tested somewhere outside a black hole horizon. That is a demanding list. The universe has made the experimental conditions inconvenient. Planck-scale physics does not happen on a laboratory bench where we can turn a dial and repeat the trial tomorrow, at least not with any technology we currently possess. Instead, nature may have hidden its quantum gravity experiments inside black holes, at the beginning of cosmic history, and perhaps in the final stages of objects that live for absurd lengths of time. We're trying to reconstruct the experiment from whatever evidence leaks into accessible physics, gravitational waves, radiation, cosmological structure, black hole thermodynamics, the behavior of quantum information, the absence of expected signals, sometimes even the absence matters, and perhaps the most important thing Planck stars reveal right now is not what lies inside a black hole. It is how carefully we have to speak when we reach the edge of established physics. We know black holes form, we've observed their effects, we've imaged horizon-scale environments, we have heard their mergers through gravitational waves, we know general relativity predicts singular behavior in gravitational collapse. We know a complete description must somehow confront quantum physics in extreme regimes. Then the certainty begins to decrease. Loop quantum gravity may provide the correct microscopic description, or it may provide only part of it. Quantum geometry may resolve singularities. A finite density bounce may occur. A black hole may transition to a white hole. A remnant may survive. One of those possibilities may eventually leave an observational signature. At present, none of those later statements has the same status as the existence of astrophysical black holes themselves. That difference is the answer. A Planck star is not something we have discovered hiding inside a black hole. It is a proposal for what might replace the part of the classical story where our current description stops making physical sense. And because the proposal now has consequences that can be studied, constrained, revised, and in some versions searched for astronomically, it belongs to physics rather than simply to imagination. The next step does not require believing in Planck stars. It requires making the models precise enough that nature can disagree with them. Future observations may reveal an unexpected transient. A population of compact remnants may be found. Black hole evaporation may eventually be understood through a deeper quantum theory. Gravitational wave measurements may constrain quantum modifications more tightly. Or every proposed Planck star signature may fail to appear, forcing researchers toward another description. Either outcome tells us something. For now, somewhere inside the mathematical description of a collapsing black hole, we still reach the place where Einstein's classical theory tells us that its own journey cannot continue in the ordinary way. Whether nature places a Planck star there, a different quantum geometry, or something for which we do not yet have a good name remains open. And until an observation or a more complete theory chooses among those possibilities, the Planck star remains exactly where it has been most useful. Not established fact, not empty speculation, but one carefully developed attempt to understand what gravity does when collapse has gone farther than classical space-time can safely follow.